Hello there and welcome to Science for Sleep, where curiosity gets cozy and the universe slows down just enough for us to wander through it together. Tonight, we are drifting into one of the strangest and quietest mysteries in all of existence. Not black holes, not exploding stars, not galaxies colliding in brilliant storms of light, but something almost opposite to all of that. Vast regions of space where almost nothing exists at all. The universe, as it turns out, is filled with enormous empty places. Not little gaps between planets or stretches of darkness between stars, but truly gigantic holes in the cosmic structure itself. Places so large that entire clusters of galaxies could disappear inside them without much trouble. Regions where the nearest galaxy might be hundreds of millions of light years away. Immense silent expanses where, if you somehow floated there, the night sky would look far darker than anything human beings have ever experienced. And the strange part is that these empty regions are not accidents or tiny flaws in the universe. They are one of its main features. In a way, the cosmos resembles an enormous sponge or perhaps a loaf of bread with bubbles baked through it. Matter gathered into glowing strands and crowded knots while other places were left strangely abandoned. Galaxies collected along invisible filaments like towns built beside rivers, while between them grew immense hollows that became larger and emptier over billions of years. It is a little unsettling when you first realize this. We often imagine the universe as crowded with stars everywhere you look, every direction packed with glittering galaxies stretching endlessly into the distance. Science fiction certainly likes to portray it that way. Spaceships darting from one civilization to another every few minutes, as though the cosmos were a busy shopping district with slightly more lasers. Reality is quieter, much quieter, much. Most of the universe is empty space. Even galaxies themselves are mostly emptiness. The atoms in your body are separated by astonishingly large relative distances. And then beyond the galaxies, beyond the clusters, beyond the bright rivers of stars, there are these gigantic cosmic voids where the loneliness becomes almost difficult to comprehend. Which raises a rather gentle but very peculiar question. Why would a universe capable of creating quasars, nebulae, planets, oceans, whales, sandwiches, and late-night online shopping also create gigantic regions of almost nothing? What purpose does emptiness serve? And perhaps even stranger, why does the universe seem to organize itself this way at all? Before we begin wandering through those enormous silent regions tonight, though, I would love to ask you something fitting for a journey about distance and darkness. Where in the world are you listening from right now? Maybe you are lying in bed while rain taps softly against the window. Maybe you're listening during a late-night drive while streetlights drift past like little artificial stars. Or perhaps it is already morning where you are, and the sky is just beginning to brighten while the rest of the world still yawns awake. And while you settle in, I also have to ask another question that feels strangely appropriate for tonight's topic. When was the last time you looked up at the night sky and really noticed how much of it is empty? Because that darkness between stars is not just background decoration, it is most of the universe. If you find these quiet little expeditions soothing or comforting after a long day, I would be ever so grateful if you gave the video a like and perhaps subscribed as well. It helps this calm corner of science drift toward other tired travellers who may need something gentle to fall asleep to. Though I should warn you, once you start thinking about cosmic voids, ordinary empty spaces may never feel quite the same again. A dark room suddenly becomes cosmological. The gap between two buildings begins to feel slightly existential. Even waiting for the microwave to finish at 2 a.m. can start to resemble floating alone between galaxies, except with fewer stars and more leftover pasta. Still, despite how eerie the idea may sound at first, cosmic voids are not violent places. They are not devouring matter like black holes or blasting radiation across the cosmos. In fact, they are almost peaceful in their emptiness. Quiet beyond imagination. Regions where very little has happened for billions upon billions of years. And yet those quiet places may hold some of the biggest clues about how the universe itself evolved. To understand why, we need to slowly adjust our sense of scale, because cosmic voids are difficult for the human mind to picture at first. Our brains evolved to navigate forests, hills, rivers, crowded cities, and occasionally the mystery of where we left our keys 5 seconds ago. We are not naturally equipped to visualize structures spanning hundreds of millions of light years. Even the word empty becomes slippery on those scales. After all, what does emptiness really mean? If you removed every planet from the solar system except Earth, space would still feel busy to us because the sun dominates everything nearby. If you removed every star except one from an entire galaxy, that galaxy would suddenly feel hauntingly sparse. But cosmic voids operate on scales so large that even galaxies themselves become rare little islands scattered across impossible darkness. The nearest neighbouring galaxy to our Milky Way, the Andromeda Galaxy, sits about 2.5 million light-years away. That distance alone is already difficult to grasp. Light, the fastest thing in the universe, takes 2.5 million years to travel between us and Andromeda. By the time its light reaches Earth, entire species have appeared and vanished here. Now imagine distances not of millions, but hundreds of millions of light-years between major concentrations of matter. That is the scale of cosmic voids, and despite their emptiness, they are not truly empty. That is another wonderfully strange detail. Even the loneliest voids still contain traces of matter. A few scattered galaxies may drift through them. Invisible dark matter still stretches faintly across their interiors. Thin gas particles wander the darkness. Radiation passes quietly through. The quantum fields of the universe continue humming away in silence. Absolute nothingness, as far as physics can tell, may not really exist. The universe seems unwilling to create perfect emptiness. Instead, voids are places of astonishing scarcity, places where matter lost the cosmic competition long ago. Because in the early universe, matter was not spread perfectly evenly. Tiny fluctuations existed almost immediately after the Big Bang. Some regions contained slightly more matter than others, not much more, just enough for gravity to begin its patient work, and gravity is very patient. Over billions of years, those slightly denser regions pulled in more and more material. Galaxies formed there. Clusters emerged. Massive filaments stretched across the cosmos like glowing strands of webbing. Meanwhile, the less dense regions gradually lost matter to their heavier neighbours. Material drifted outward toward the crowded areas, leaving behind expanding emptiness. The rich regions became richer. The empty regions became emptier. In other words, cosmic voids formed partly because gravity is unfair. The universe, rather rudely, allowed some neighbourhoods to collect almost everything while others were left astonishingly bare. Cosmic urban planning, it seems, can be deeply uneven. What fascinates astronomers is that these voids are not random holes punched into space. They form patterns. Giant interconnected bubbles woven throughout the cosmic web. When scientists map the large-scale structure of the universe, it resembles foam or lace, or the branching structure of neurons in a brain. Dense galaxy clusters sit at the intersections, while enormous voids occupy the spaces between them. And somehow, this arrangement emerged naturally from the laws of physics. No architect designed it. No cosmic gardener trimmed the galaxies into shape. The universe simply evolved this way on its own. There is something oddly calming about that. Out of pure gravity, time, expansion, and tiny fluctuations in matter, came a structure so immense that human beings only discovered it recently. For most of history, we had no idea these giant holes existed at all. When ancient humans looked up at the stars, the sky appeared richly populated. Even with early telescopes, astronomers mostly saw isolated galaxies scattered around the heavens. It was not until the 20th century, when surveys became large enough to map enormous portions of the cosmos, that scientists noticed something peculiar. the galaxies were not evenly distributed. Instead, they formed long walls and filaments surrounding huge empty regions. At first, some astronomers found this deeply surprising. Others found it slightly alarming. There is always something unsettling about discovering that reality is structured differently than expected. Rather like realizing your tidy kitchen drawer is actually a portal to an alternate dimension made entirely of tangled cables and expired batteries. One of the first major discoveries came in the late 1970s when astronomers identified the Bhuta's Void, an enormous empty region roughly 330 million light-years across. To give you some perspective, our entire Milky Way galaxy spans about 100,000 light-years. The Bhuta's Void is thousands of times larger, and inside it, almost nothing. A few scattered galaxies drift through the darkness, but compared to surrounding regions it is astonishingly barren. If the Milky Way were placed inside the Bhuta's Void, the nearest major galaxies would lie unimaginably far away. The night sky would appear sparse and dim in ways difficult for humans to emotionally process. Earth's sky, even in remote deserts, still glows with thousands of visible stars because we live inside a galaxy crowded with them. But in certain regions of a cosmic void, the heavens themselves would feel abandoned. No bright river of the Milky Way overhead, no nearby galactic neighbours, just darkness with occasional faint smudges of distant light. And yet, these empty places are essential to the structure of the universe itself. Without voids, the cosmic web would not exist. The dense regions depend on the empty ones, almost like bubbles in rising bread dough. One cannot form without the other. There is also a curious emotional reaction many people have when they first learn about cosmic voids. Some find them frightening, others find them peaceful. A few immediately start imagining alien civilizations hiding there, which admittedly says quite a lot about humanity. But perhaps the most interesting response is wonder, because cosmic voids remind us that the universe is not designed according to human expectations. We instinctively associate importance with things, objects, events, movement, noise, yet the cosmos dedicates enormous portions of itself to silence and emptiness. And still, those empty regions shape everything around them. Galaxies move partly because of voids. Light bends around their structure. The expansion of the universe interacts with them. Even our understanding of dark energy may depend partly on studying these giant holes, which means emptiness is not absence. Emptiness has consequences. A strange thought, really? Sometimes what is not there matters just as much as what is. You can see this even in ordinary life. A pause in conversation changes meaning. An empty seat at table feels emotionally significant. A quiet street at night feels entirely different from a crowded one. Space itself alters experience. The universe seems to understand this principle on scales beyond imagination. And tonight, as we slowly drift deeper into these enormous silent regions, we will begin exploring how astronomers discovered them, why gravity created them, what might actually exist inside them, and why these giant holes could reveal some of the deepest truths about the cosmos itself. Because surprisingly enough, studying nothing may turn out to be one of the best ways to understand everything. For a very long time, astronomers assumed the universe was, more or less, evenly populated. Not perfectly uniform, of course. Even early skywatchers understood that stars gathered into clusters and that galaxies came in different shapes and sizes. But on the largest scales, most scientists expected matter to spread out fairly smoothly across the cosmos, like grains of sand scattered across a beach. That assumption felt reasonable. After all, when you look up at the night sky with your own eyes, stars appear everywhere. Even in darker regions between constellations, there are always more stars waiting just beyond human vision. Early telescopes only reinforced this impression. Every improvement in astronomy revealed additional objects, more stars, more nebulae, more galaxies. The universe seemed endlessly crowded, And honestly, humans have a habit of assuming that if something looks evenly spread from our perspective, it probably continues that way forever. We do this all the time. Stand in a forest and it feels infinite. Look across the ocean and it appears endless. Open your kitchen junk drawer and somehow it contains 17 charging cables, despite owning approximately 3 electronic devices. Scale changes perception. The deeper astronomers looked into space during the 20th century, the more they realized the universe was not arranged the way anyone expected. At first, the clues were subtle. In the 1920s, Edwin Hubble demonstrated that galaxies existed far beyond the Milky Way. Before that discovery, many astronomers thought our galaxy might actually be the entire universe, which in hindsight is a wonderfully human misunderstanding. Every civilization tends to assume it occupies the center of everything until evidence gently taps it on the shoulder and says, actually, no. Suddenly the cosmos became vastly larger. Instead of one galaxy, there were billions. And once astronomers began cataloguing galaxies in serious numbers, patterns slowly emerged. Some regions contained enormous concentrations of galaxies clustered together like cosmic cities. Other areas appeared strangely sparse. At first, scientists assumed this was probably observational bias. Telescopes had limitations. Dust obscured certain regions. Survey methods were incomplete. But as technology improved throughout the mid-20th century, the pattern refused to disappear. In fact, it became more obvious. Galaxies were not spread evenly across space at all. They formed structures, long chains, sheets, clusters, massive interconnected arrangements spanning unimaginable distances. And between them lay something strange, gigantic regions with very few galaxies. The realization arrived gradually rather than dramatically. Science often works this way. There is rarely a single moment where somebody dramatically gasps while staring through a telescope and drops their teacup in existential shock. Most discoveries emerge through years of measurements, arguments, statistical analysis, and exhausted researchers staring at charts while wondering whether the universe is broken or whether they simply forgot to calibrate something again. Still, certain moments stood out. One of the earliest major hints came during galaxy redshift surveys. These surveys measured not only where galaxies appeared in the sky, but how far away they were. This was crucial because a flat sky map can be misleading. 2 galaxies might appear close together from Earth's perspective, while actually sitting millions of light years apart. Redshift measurements changed everything. By studying how light stretched as galaxies moved away from us due to cosmic expansion, astronomers could begin constructing 3-dimensional maps of the universe. Suddenly, the cosmos gained depth, and that depth revealed gaps, enormous gaps. In the 1970s, astronomers Stephen Gregory and Laird Thompson began noticing unexpectedly large empty regions while mapping galaxy distributions. Their observations hinted that galaxies formed enormous superclusters surrounding suspiciously underpopulated areas. Then came one of the biggest turning points in cosmic cartography. In 1981, astronomer Robert Kirshner and his colleagues announced the discovery of what became known as the Bhuta's Void. Even today, the Bhuta's Void sounds slightly fictional, like a location where science fiction heroes accidentally awaken ancient machines or discover a drifting civilization powered entirely by philosophical regret. Instead, it turned out to be something arguably stranger. A truly gigantic region of space containing astonishingly few galaxies. The void spans roughly 330 million light-years across. To appreciate how absurdly large that is, remember that light itself, travelling at nearly 300,000 kilometers per second, requires 330 million years to cross it. Dinosaurs appeared and vanished on Earth during shorter spans of time. Human civilization is microscopic compared to such distances. Inside this enormous region, astronomers expected to find thousands upon thousands of galaxies. Instead, they found very few. The discovery genuinely surprised scientists, not because emptiness itself was impossible, but because the scale of the emptiness seemed almost unreasonable. The Buddha's void was so large that it challenged assumptions about how matter organized itself in the universe. And perhaps more unsettlingly, it implied the cosmos might resemble foam or bubbles rather than a smooth distribution. The universe, it seemed, had holes, big ones. As additional surveys expanded through the 1980s and 1990s, astronomers realized the Buddha's void was not unique. Cosmic voids existed everywhere. Some smaller, some larger, all woven into a gigantic structure now called the cosmic web. This web-like arrangement became one of the most important discoveries in modern cosmology. Matter gathered into enormous filaments stretching across space like glowing threads. At their intersections sat galaxy clusters containing hundreds or thousands of galaxies. Surrounding them sprawled enormous empty regions where comparatively little matter existed. Imagine soap bubbles pressed together in a sink. The thin surfaces where bubbles touch resemble the dense galaxy filaments. The hollow interiors resemble cosmic voids. Or think about bread dough rising in an oven. The bread itself forms around expanding pockets of air. Likewise, galaxies gathered around expanding regions of emptiness. The comparison sounds oddly domestic for something involving billions of galaxies, but honestly, the universe has no obligation to resemble our expectations. Sometimes the largest structures in existence end up looking suspiciously like breakfast. Astronomers began producing increasingly sophisticated maps of this structure. One especially famous effort was the CFA Redshift Survey, conducted by the Harvard-Smithsonian Center for Astrophysics. When scientists plotted galaxy positions from the survey, the results stunned people. The universe looked almost biological. Filaments stretched outward like neurons in a brain or roots, spreading through soil. Dense walls of galaxies enclosed giant empty cavities. One enormous structure called the Great Wall extended across more than 500 million light-years. And between those walls, darkness, immense cosmic silence. What made these discoveries particularly fascinating was that they aligned beautifully with theories about gravity and the evolution of the early universe. The cosmos did not begin with galaxies already formed. Shortly after the Big Bang, matter existed as a hot, dense plasma spread nearly evenly throughout space. But nearly evenly is not perfectly evenly. Tiny fluctuations existed from the very beginning. Some regions were slightly denser than others. Gravity amplified those differences over billions of years. Denser regions pulled in more material. Sparse regions lost material to their surroundings. Eventually, matter organized itself into the cosmic web astronomers now observe, which means voids formed naturally as matter migrated away from them. The empty places became emptier. There is something strangely elegant about this process. The universe did not carve holes intentionally. Gravity simply spent billions of years rearranging matter until giant gaps emerged automatically. Like dust collecting into corners of a room, or people unconsciously clustering near snacks at parties, while certain awkward corners remain mysteriously abandoned all evening. Given enough time, structure emerges. What also fascinated astronomers was how difficult cosmic voids could be to detect directly. Humans are very good at noticing objects. We are less naturally equipped to notice absences. You immediately notice a bright city skyline. You rarely pause to admire the empty countryside surrounding it. Likewise, early astronomers focused primarily on galaxies themselves because galaxies emit light. Voids do not. Detecting emptiness requires understanding the distribution of everything around it. In a sense, scientists discovered cosmic voids indirectly by realizing where galaxies were not. This sounds simple, but it required enormous data sets. You cannot identify a giant hole unless you first map the surrounding structure carefully enough to recognize the missing region. And gathering those measurements was painstaking work. Today, Computer simulations make these structures look almost obvious. Cosmologists generate immense virtual universes showing matter evolving into filaments and voids over billions of years. Modern galaxy surveys map millions of objects automatically. But decades ago, much of this work involved painstaking observations recorded one galaxy at a time, thousands upon thousands of measurements. Astronomy, despite its glamorous reputation involving stars and cosmic mysteries, frequently consists of researchers spending long nights analysing faint smudges while consuming heroic quantities of coffee. Sometimes science advances through dramatic inspiration. Sometimes it advances because someone stubbornly catalogues galaxies for 15 years. As observations improved, scientists also realised voids were not completely empty. A few galaxies still drift through them. These are usually smaller, fainter galaxies compared to the crowded giants found in dense clusters. That detail turned out to matter enormously, because the galaxies inside voids evolved differently. Without frequent collisions or gravitational interactions, void galaxies often remained relatively isolated for billions of years. Studying them became like examining cosmic nature preserves, where evolution unfolded more quietly than in crowded galactic cities. This allowed astronomers to compare how galaxies behave in different environments, and once again, emptiness became scientifically valuable. There is a recurring theme in astronomy, where apparently unimportant regions suddenly become essential to understanding everything else. Dark matter itself was discovered partly because galaxies behaved strangely. Black holes were inferred before they were observed directly, and cosmic voids, despite containing comparatively little matter, became powerful tools for studying the universe. Even dark energy, the mysterious force driving cosmic expansion, may leave detectable signatures in the behaviour of voids. The emptiest places in existence help scientists understand the fate of the cosmos itself, not bad for regions defined mostly by absence. One particularly eerie realisation emerged as astronomers studied larger and larger cosmic scales. The universe transitions from clumpy to smooth only at extremely large distances. Locally, everything is uneven. Galaxies cluster, voids expand, matter forms enormous patterns. Only when averaging across truly colossal scales does the universe begin resembling the homogeneous cosmos predicted by early cosmological theories. That distinction matters because it changed how scientists thought about the architecture of reality itself. The universe was not simply filled with galaxies scattered randomly through infinite darkness. It possessed structure, texture, geometry, a kind of enormous cosmic geography, and humans had only just begun discovering it. There is something deeply humbling about that realization. For most of human history, we knew nothing about galaxies. Then we discovered galaxies but not cosmic structure. Then we discovered the cosmic web but not dark energy. Every generation uncovers another layer. Reality keeps turning out larger and stranger than expected, and perhaps that is one reason cosmic voids fascinate people so much. They represent not only physical emptiness, but conceptual emptiness as well. They remind us how recently humanity realized the universe has architecture on scales beyond ordinary comprehension. The sky above ancient civilizations looked exactly the same as ours. Yet they had no idea those stars belonged to a galaxy suspended inside a vast web surrounding giant holes millions of light years wide. Even now, most people rarely think about it. You go grocery shopping, you answer emails, you wonder whether the laundry has been sitting in the washing machine too long. Meanwhile, our entire galaxy drifts along a filament bordering gigantic cosmic voids that stretch across unimaginable darkness. Reality is wonderfully strange when viewed from the correct angle, and the more astronomers mapped the universe, the stranger it became. By the late 20th century, surveys like the Sloan Digital Sky Survey began producing breathtakingly detailed maps of galaxy distributions. Millions of galaxies revealed an increasingly intricate cosmic web. The patterns were unmistakable. The universe resembled lace, foam, a network of glowing rivers separated by oceans of emptiness. At that point, cosmic voids transformed from curious anomalies into one of the defining features of cosmology itself. Scientists no longer asked whether voids existed. They began asking why the universe produced them so naturally, and perhaps more importantly, what those empty places might reveal about the invisible forces shaping everything around us. By this point in our journey, we know that the universe contains gigantic empty regions stretching across astonishing distances. We know astronomers discovered them gradually while mapping galaxies across space, but now we arrive at an important question, and honestly, it is one of those questions that sounds simple right up until you try answering it properly. What exactly counts as a cosmic void? After all, space itself is already mostly empty. Even the region around Earth is largely vacuum. The nearest planet is tens of millions of kilometers away most of the time. The nearest star beyond the Sun sits more than 4 light-years from us. Galaxies are separated by even greater distances, so when astronomers say a region is empty, what do they actually mean? Well, surprisingly enough, cosmic voids are not simply ordinary empty space scaled up to ridiculous proportions. They are specific structures within the large-scale architecture of the universe. They are regions where the density of matter is dramatically lower than the cosmic average. That last part matters. A void is not defined by absolute emptiness. It is defined by comparison. Imagine standing inside a crowded city at rush hour. Cars everywhere. People crossing streets. Buildings packed tightly together. Now imagine driving outward into rural countryside where houses become sparse and long stretches of open land separate small towns. The countryside is not literally empty. There are still roads, farms, animals, perhaps one deeply suspicious gas station with flickering lights and exactly 3 bananas for sale. But compared to the city, it feels empty. Cosmic voids work similarly. The universe contains regions where galaxies crowd together densely, enormous clusters packed with thousands of galaxies interacting gravitationally. Meanwhile, voids contain far fewer galaxies than expected for their size, sometimes dramatically fewer. A typical cosmic void may span tens or hundreds of millions of light-years, while containing only a tiny fraction of the galaxies found in denser regions. And what makes this especially strange is the sheer scale involved. On Earth, we experience emptiness locally, an empty room, a quiet road, a desert valley. But cosmic voids are so enormous that the mind struggles to emotionally process their dimensions. Let's try anyway. Our Milky Way galaxy contains somewhere between 100 and 400 billion stars depending on the estimate. It spans roughly 100,000 light-years across, already enormous. Now imagine placing the Milky Way inside a cosmic void. Not near the edge, not beside neighbouring galaxy clusters, right in the middle. Suddenly, the nearest major galaxies might lie hundreds of millions of light-years away in every direction. The night sky would barely resemble the one humans know. This is important because our sky is unusually bright compared to what many regions of the universe might experience. We live inside a galaxy rich with stars. We also have nearby neighbouring galaxies. Even distant galaxies contribute faint background light, but deep inside a large void the heavens could appear hauntingly sparse. Few bright galaxies, very little structure, mostly darkness. The cosmic web would seem unimaginably far away, like isolated islands beyond an endless ocean. And yet, even there, the void would not be truly empty. This is one of the most important things to understand about cosmic voids. They still contain matter, just much less of it. Tiny amounts of gas drift through them. Dark matter remains present, though at lower densities. Radiation crosses silently through space. Occasionally small isolated galaxies appear inside the voids themselves. In fact, some void galaxies are among the most fascinating galaxies astronomers study because they evolved under unusually isolated conditions. Imagine growing up in the middle of nowhere, cosmologically speaking. No neighbouring galaxies constantly colliding with you. No crowded cluster tugging gravitationally on your structure. No frequent galactic traffic jams. Void galaxies tend to live quieter lives. Many are smaller, bluer, and still actively forming stars because they avoided the violent interactions common in denser regions. Astronomers sometimes compare them to remote villages untouched by the chaos of crowded cities. The universe, it turns out, has galactic countryside. Of course, the word void still sounds dramatic because humans associate emptiness with danger or mystery. We instinctively dislike large empty spaces. Evolution probably encouraged this. Vast emptiness on ancient Earth often meant exposure, vulnerability, lack of resources, or the possibility that something large and hungry was quietly watching from somewhere inconvenient. Space amplifies that discomfort enormously. Even ordinary interstellar space feels unsettling when considered carefully. The vacuum between stars is already more empty than anything humans naturally encounter, but cosmic voids elevate that emptiness to absurd levels, and yet, strangely enough, they are also incredibly important. Without voids, the universe would not have its current structure at all. To understand why, we need to picture the cosmos less like scattered dots and more like a gigantic interconnected network. Astronomers call this structure the cosmic web. Galaxies are not randomly distributed through space. They gather into filaments stretching across hundreds of millions of light years. These filaments intersect at massive galaxy clusters. Between them sit expanding voids. If you could somehow zoom far enough away from the observable universe, the structure might resemble soap foam or the branching veins of a leaf. Matter collected into strands, emptiness expanded between them, and importantly, the voids continue evolving even today. That surprises many people. We tend to imagine emptiness as static, but cosmic voids are dynamic structures. Over billions of years, matter slowly flows outward from low-density regions toward denser areas under gravity's influence. The rich regions become richer, the empty regions become emptier. It is essentially the universe conducting long-term cosmic urban migration. Galaxies drift toward crowded regions while voids expand and thin out further over time. In a sense, cosmic voids are not simply holes punched into the universe. They are regions that lost the competition for matter. Gravity favoured denser neighbourhoods. The sparse regions gradually emptied. And because the universe itself expands, the voids also grow larger as space stretches. There is something oddly peaceful about this process. No explosions required, no dramatic destruction, just billions of years of slow cosmic rearrangement. The universe can accomplish extraordinary things through patience alone. Astronomers classify voids by size and density. Smaller voids may span only a few million light years, while giant supervoids stretch hundreds of millions of light years across. Some are relatively shallow with scattered galaxies still drifting through them. Others are extraordinarily underdense, approaching the emptiest large-scale environments known. One particularly interesting detail is that voids are not perfectly spherical. Early descriptions sometimes made them sound like giant empty bubbles floating through space. Reality is messier. Voids stretch and deform under gravitational influences from surrounding structures. They merge with neighbouring voids. They evolve over time. Their boundaries can appear fuzzy because matter density changes gradually rather than ending abruptly. The edges of a void are not walls. You do not suddenly cross a glowing cosmic border labelled now entering extreme emptiness. Instead, galaxy density slowly decreases as you move inward. This makes defining exact boundaries surprisingly difficult. Astronomers use statistical methods and density thresholds to identify voids in galaxy surveys, which means cosmic voids are partly observational categories rather than perfectly clean geometric objects. The universe rarely organises itself according to tidy human labels. Even galaxies themselves are messier than textbook diagrams suggest. Planets wobble. Stars behave strangely. Black holes produce jets capable of crossing entire galaxies. Somewhere right now, an astronomer is probably staring at unexpected data while muttering, "Well, that seems inconvenient." Cosmic voids fit nicely into this tradition. Still, despite their complexity, they reveal something profound about how structure emerged after the Big Bang. Shortly after the universe formed, matter was distributed remarkably evenly overall, but not perfectly evenly. Tiny fluctuations existed in density. Some regions held slightly more matter than average, others slightly less. Gravity amplified those tiny differences. Denser regions attracted additional matter. Underdense regions lost matter outward. Over billions of years, this process sculpted the cosmic web. So in a way, cosmic voids are fossils of the universe's earliest irregularities. They preserve information about conditions shortly after the Big Bang itself. That makes them incredibly valuable scientifically. By studying voids, astronomers can test cosmological models and measure how matter evolved over time. Voids also help scientists investigate dark matter and dark energy, two of the biggest mysteries in physics. Dark energy especially influences void growth because it affects how rapidly space expands. Some researchers even call voids cosmic laboratories because their relative emptiness makes certain large-scale effects easier to observe, which is wonderfully ironic. The emptiest places in existence became some of the most useful tools for understanding the universe. Another fascinating aspect of cosmic voids is how they influence light itself. As light travels across billions of light years, it passes through dense galaxy clusters and sparse void regions. These structures subtly affect the light's energy and trajectory. For instance, photons traveling through expanding voids can experience slight energy changes due to cosmic expansion and gravitational effects. Astronomers study these distortions carefully because they provide clues about how the universe evolves. Even emptiness leaves fingerprints. That idea feels strangely philosophical without actually being philosophical. Absence changes reality. Space shapes motion. The regions where little exists still influence everything around them. You see smaller versions of this principle constantly in ordinary life. An empty seat at dinner changes the mood of a table. A silent pause changes conversation. A gap in music creates tension. Structure depends partly on what is missing. The cosmos seems to understand this instinctively, and the more astronomers map the universe, the more obvious this becomes. Modern surveys now reveal thousands upon thousands of voids woven throughout the observable universe. Sophisticated computer simulations reproduce similar structures with astonishing accuracy. The cosmic web appears naturally when gravity acts on matter over immense spans of time, which means giant holes in the universe are not unusual accidents. They are expected outcomes of cosmic evolution. That realization changed astronomy profoundly. Early astronomers often imagined the universe as relatively smooth on the larger scales. Today we understand it more like a living network constantly evolving under gravity and expansion. Matter streams along filaments, clusters collide, voids expand, galaxies drift slowly through an architecture larger than anything human beings evolved to comprehend intuitively. And somewhere inside one tiny spiral galaxy, near the edge of an ordinary filament, a species emerged that eventually noticed the pattern. Honestly, that may be one of the strangest parts of the story. The universe built structures spanning hundreds of millions of light years, then produced creatures small enough to fit comfortably on sofas who somehow figured out those structures existed at all. Not quickly either. It took centuries of observations, better telescopes, redshift measurements, massive surveys, and astonishing mathematical effort. Also, humanity could eventually discover that much of reality consists of enormous cosmic emptiness. There is something almost humorous about that outcome. We searched the heavens expecting endless galaxies and found giant holes instead. And perhaps the strangest thing of all is that those holes are not flaws in the universe, they are part of its design. Not intentional design, of course, more like natural architecture emerging from gravity, time and expansion. The cosmos organising itself according to physical laws until patterns appeared. And among those patterns, voids became some of the largest structures ever discovered. Huge silent regions drifting between rivers of galaxies, ancient expanses where comparatively little has happened for billions of years, places so empty that they redefine what emptiness itself can mean. Yet the deeper scientists study them, the more they realise these giant holes may hold answers to questions far bigger than the voids themselves. One of the strangest realisations in modern astronomy is that the universe, despite appearing random at first glance, is actually organised into an enormous hidden structure. Not a rigid structure, not neat rows or perfect symmetry. More like a sprawling cosmic network that emerged naturally over billions of years, shaped by gravity, dark matter, expansion, and time itself. And the truly peculiar thing is that if you zoom out far enough, galaxies stop looking like isolated islands and begin resembling something closer to veins, roots, or threads stretched across unimaginable darkness. The universe is not evenly spread out. Matter gathered into patterns. At first, this idea feels counterintuitive because from Earth's perspective, the night sky appears fairly uniform. Stars are scattered everywhere. Galaxies show up in every direction. Space seems busy enough, but human beings are not very good at intuitively grasping large-scale cosmic structure. Our brains evolved to notice nearby things that mattered for survival. Food sources, storm clouds, predators. Whether or not somebody else in the village accidentally took the good cooking pot again, the cosmos operates on scales so enormous that intuition becomes unreliable remarkably quickly. Imagine flying high above Earth at night. At ground level, cities seem isolated and separate, but from above, roads begin connecting them. Patterns emerge, networks form. Dense urban centres glow brightly, while vast dark regions stretch between them. Now scale that concept upward beyond comprehension. Galaxies are not evenly scattered like random grains of dust. They gather into enormous systems connected by gigantic filaments. These filaments stretch across hundreds of millions of light years, intersecting at massive galaxy clusters while surrounding immense cosmic voids. Astronomers call this arrangement the cosmic web. And honestly, it is one of the most beautiful names in science because it describes the structure surprisingly well. If you look at modern computer simulations of the universe, the resemblance to a web becomes unmistakable. Long glowing strands intersect and branch outward, while dark, hollow regions expand between them. Sometimes it resembles neural tissue, sometimes soap bubbles, sometimes roots spreading through soil. Occasionally it looks suspiciously like the universe spilled coffee on itself and decided to keep the pattern. What matters is that this structure was not designed deliberately. No cosmic architect arranged galaxies into place. The web emerged naturally from simple physical processes acting over immense periods of time, which is somehow even more impressive. To understand why matter became unevenly distributed, we need to travel backward to the early universe shortly after the Big Bang. At that time, the universe was astonishingly smooth overall. Matter and energy spread through space in an incredibly hot, dense state. If you could somehow observe it directly, it would appear remarkably uniform, but not perfectly uniform. Tiny fluctuations existed almost immediately. Some regions contained slightly more matter than others. We're talking about incredibly small differences here. Variations so tiny they might initially seem meaningless. Gravity disagreed. Gravity notices everything. A region containing just a little extra matter exerts slightly stronger gravitational attraction. Over time, it pulls in surrounding material. As it gains more matter, its gravity strengthens further, attracting even more. Meanwhile, regions with slightly less matter gradually lose material outward toward denser areas. This process repeated endlessly across the young universe. Dense regions became denser. Sparse regions became emptier. Eventually, the first stars formed, then galaxies, then clusters of galaxies. Over billions of years, matter organized itself into the cosmic web astronomers observe today, which means the universe did not begin clumpy. It became clumpy, and those clumps grew into structures so enormous that light itself requires hundreds of millions of years to cross them. There is something oddly satisfying about this process, because it shows how complexity can emerge from incredibly simple rules given enough time. Gravity pulls, matter moves, structure forms, no instructions required. This same basic principle appears everywhere in nature. Snowflakes organize themselves from molecular interactions. Rivers carve branching systems through landscapes. Sand dunes align into patterns shaped by wind. The universe simply performed this process on scales beyond human imagination. One especially important ingredient in all of this is dark matter. Now, dark matter sounds dramatic, almost like something hidden in a secret laboratory beneath a volcano guarded by suspiciously polite robots. In reality, it is one of the biggest unsolved mysteries in physics. Astronomers cannot see dark matter directly because it does not emit or absorb light, but they know it exists because its gravity affects visible matter. Galaxies rotate too quickly for their visible mass alone to hold them together. Galaxy clusters contain far more gravitational pull than ordinary matter can explain, and the cosmic web itself formed largely because dark matter created invisible scaffolding throughout the universe. In fact, ordinary matter, the atoms making up stars, planets, tea kettles, penguins, and every human who has ever accidentally walked into the wrong room and forgotten why, represents only a small fraction of the universe's total matter content. Dark matter dominates gravitational structure. Computer simulations show that dark matter gathered first into enormous filamentary structures. Ordinary matter then followed those gravitational pathways, cooling into galaxies and clusters. So beneath the visible universe lies an invisible framework shaping everything around us, which is wonderfully unsettling if you think about it too long before bed. We live inside a structure largely governed by matter we still do not fully understand, and yet somehow human beings discovered this by observing faint smudges of light through telescopes while standing on a rocky planet orbiting an ordinary star. That alone feels mildly miraculous. As astronomers mapped larger portions of the universe, the scale of the cosmic web became increasingly obvious. Galaxy clusters sit at intersections like knots in a net. Filaments stretch outward, connecting them across vast distances. Voids expand between them like gigantic bubbles. One famous structure called the Sloan Great Wall spans approximately 1.4 billion light-years. Another structure known as the Hercules Corona Borealis Great Wall may stretch even farther, though scientists still debate aspects of its true scale. These are among the largest known structures in existence, and yet despite their immensity, they emerged naturally from tiny fluctuations present shortly after the Big Bang. There is something deeply calming about the patience of cosmic evolution. Human beings tend to expect dramatic events, sudden transformations, immediate results. We grow frustrated waiting for elevators. Meanwhile, the universe spends billions of years slowly organizing matter into structures spanning incomprehensible distances without the slightest concern for efficiency. Cosmic architecture unfolds very slowly. Another important realization is that galaxies themselves are not distributed randomly even within filaments. Gravity continues shaping structure on smaller scales too. Galaxies form groups, groups form clusters, clusters merge into superclusters. Everything exists within larger contexts. The Milky Way belongs to a small collection called the Local Group, which includes Andromeda and dozens of smaller galaxies. The local group belongs to the Virgo supercluster, and that supercluster itself forms part of an even larger structure called Laniakea. The name Laniakea means immense heaven in Hawaiian, which honestly feels appropriate because it contains roughly 100,000 galaxies spread across hundreds of millions of light years. And even Laniakea exists merely as one region within the broader cosmic web. The scale becomes difficult to emotionally absorb at this point. The human brain starts quietly waving a white flag somewhere around hundreds of millions of light years. Still, what matters most is the pattern. The universe has texture. It has shape. Matter collected into rivers and knots rather than spreading smoothly through space, and those patterns influence everything. Galaxies move according to gravitational flows within the cosmic web, gas streams along filaments. Galaxy collisions occur more frequently in dense environments. Even the growth of supermassive black holes depends partly on where galaxies reside within this enormous structure. Location matters cosmologically. A galaxy born inside a crowded cluster experiences a violent life full of interactions and mergers. A galaxy drifting inside a sparse region evolves more quietly. The universe has neighborhoods, some bustling, some isolated, some astonishingly empty. There is also an interesting psychological effect when people first encounter visualizations of the cosmic web. Many immediately compare it to biological systems, neural networks, blood vessels, tree roots. This resemblance is mostly coincidence because different physical systems often produce similar branching structures. Still, it creates an eerie feeling that reality repeats certain patterns across wildly different scales. Tiny neurons in a brain, gigantic filaments between galaxies, both connected by networks through which energy and information flow. Scientists remain careful not to overstate these similarities, of course. The universe is not literally a giant brain floating through space contemplating existential questions about quasars and leftover pizza. Probably. But the visual resemblance reminds us that nature often favours similar structural solutions when simple forces operate over time. Patterns emerge. And once astronomers recognised the cosmic web clearly, it transformed cosmology entirely. Before these discoveries, many models treated the universe as relatively smooth at large scales. Today, researchers understand that structure formation is one of the defining processes shaping cosmic evolution. The universe is dynamic, matter flows, voids expand, galaxies gather into rivers of gravity stretching across the darkness. Even more fascinatingly, the cosmic web continues evolving right now. Galaxies still move along filaments toward denser regions. Clusters continue merging. Voids continue growing emptier as matter drifts outward. Nothing is frozen in place. The universe remains under construction. Of course, these changes occur on timescales so enormous that humans perceive the cosmos as static. Entire civilizations rise and fall during intervals insignificant compared to galactic motion. Even stars themselves live and die while the broader cosmic web evolves slowly around them. There is something strangely comforting about that scale difference. Human problems often feel enormous because we experience them locally and immediately. But cosmology gently reminds us that reality unfolds across distances and timescales almost impossible to fully comprehend. The universe is vast enough to contain extraordinary complexity and extraordinary emptiness simultaneously. And despite all this structure, one detail still surprises many people. The cosmic web is incredibly fragile in terms of density. The filaments connecting galaxy clusters sound solid in description, but even dense cosmic structures remain mostly vacuum. Galaxies themselves are tiny compared to the distances separating them. If the Milky Way were reduced to the size of a coin, neighbouring galaxies might lie kilometres away. Most of the universe remains overwhelmingly empty even inside its densest structures, which means cosmic voids are not strange exceptions to a crowded universe. Emptiness dominates reality. Matter simply gathered into thin, interconnected strands surrounded by vast regions of near-nothingness. The visible cosmos resembles a delicate glowing skeleton suspended inside gigantic darkness, and somehow inside one ordinary spiral galaxy, drifting along one modest filament among countless others, human beings evolved enough curiosity to map the entire structure. That may be the strangest thing of all. We are tiny creatures living inside a small galaxy on the edge of an ordinary cosmic neighborhood. Yet we discovered that the universe organizes itself into structures spanning billions of light years. Not because those structures were obvious, but because humans kept asking questions. Why are galaxies distributed this way? Why do some regions appear empty? Why does matter gather into filaments? Those questions eventually revealed one of the deepest truths about the cosmos. The universe is not random scatter, it is connected. And once you begin seeing the cosmic web, it becomes impossible to imagine the universe the old way ever again. At first glance, cosmic voids almost seem backwards. If gravity pulls matter together, then why would it create enormous empty regions at all? Shouldn't gravity eventually gather everything into one gigantic crowded mess? A universal traffic jam of stars, galaxies, and highly inconvenienced black holes? The answer lies in the fact that gravity does not pull equally everywhere. And once tiny imbalances appear, gravity has a habit of exaggerating them over time, a very long time. To understand how giant empty regions formed accidentally, we need to go back once more to the early universe, when everything was much smaller, hotter, and strangely smooth. Not perfectly smooth, of course. That detail matters enormously. Shortly after the Big Bang, the universe was filled with an intensely hot plasma, made of particles and radiation packed together so tightly that light itself could barely travel freely. Matter had not yet organized into stars or galaxies. There were no planets, no clusters, no cosmic voids, just an expanding sea of energy and particles. If you could somehow observe the young universe at that stage, it would look surprisingly uniform overall. But hidden inside that smoothness were tiny fluctuations in density. Certain regions contained slightly more matter than average, others slightly less. And when I say slightly, I truly mean tiny differences. The fluctuations measured in the early universe were incredibly small, differences of perhaps 1 part in 100,000. Human beings tend to ignore differences that subtle. Gravity does not. Gravity is astonishingly persistent. A slightly denser region exerts slightly stronger gravitational pull. That extra pull attracts surrounding matter. As more matter arrives, gravity strengthens further. More material flows inward. The process feeds itself continuously over billions of years. Meanwhile, the less dense regions slowly lose matter to their surroundings. Imagine rainwater running across uneven ground. Even tiny slopes eventually guide enormous amounts of water into valleys, while higher areas dry out. The universe behaved similarly. Matter flowed toward dense regions. Sparse regions emptied further. Eventually the denser areas formed galaxies and clusters, while the underdense areas evolved into cosmic voids. So in a very real sense, voids formed not because something pushed matter away violently, but because gravity quietly pulled matter elsewhere. That distinction matters. Cosmic voids are not carved out like tunnels blasted through rock. They are leftovers, regions that gradually lost the competition for matter. Gravity accidentally abandoned them. There is something strangely human about this process. People naturally gather in areas with resources and connections. Cities grow larger while isolated rural regions sometimes lose population over time. Busy neighborhoods attract more businesses, which attract more people, which attract even more growth. Meanwhile, quieter places grow quieter. The universe built something remarkably similar on cosmic scales. Galaxies migrated toward gravitational population centers. Voids became increasingly isolated, And all of this happened slowly enough that the universe itself probably never noticed. One especially important piece of this story involves dark matter, because without dark matter, the cosmic web likely would not exist in its current form. Ordinary matter alone, the atoms making up stars and planets, does not account for enough gravity to explain large-scale structure formation properly. Dark matter provided additional gravitational scaffolding that helped matter organize more rapidly after the Big Bang. In the early universe, dark matter began clumping together first. Unlike ordinary matter, which interacted strongly with radiation, dark matter could collapse into structures more efficiently. Over time, it formed vast invisible concentrations stretching across space. Ordinary matter then followed those gravitational pathways. Gas collected inside dark matter halos. Stars formed. Galaxies emerged. Clusters grew. And between those growing structures, the emptier regions became emptier still. This process created what cosmologists sometimes call gravitational instability. Slight density differences naturally amplify over time under gravity's influence. The richer regions become richer. The emptier regions become emptier. It sounds almost unfair. And honestly, it kind of is. The universe did not distribute matter evenly after those tiny fluctuations appeared. Gravity amplified inequalities relentlessly across billions of years until enormous structures emerged. Some regions inherited giant clusters containing thousands of galaxies. Others became immense deserts of darkness. Cosmology occasionally resembles real estate economics in deeply unsettling ways. What makes this even more fascinating is that voids themselves actively influence surrounding matter as they grow. People often think of empty space as passive, but cosmic voids affect the motion of galaxies around them. Imagine a crowded room where people gradually gather into groups. As clusters form, the spaces between them naturally widen. Movement flows outward from emptier areas toward denser ones. Similarly, galaxies near voids tend to drift away from them because surrounding dense regions exert stronger gravitational attraction. The voids effectively expand over time, not because they are pushing things away directly, but because gravity elsewhere pulls matter outward more strongly. This creates a remarkable effect. Cosmic voids become self-reinforcing. Once a region becomes underdense, it loses matter more easily. As it loses matter, its gravitational pull weakens further. More material escapes towards surrounding filaments and clusters. The emptiness deepens. Over billions of years, small sparse regions merge into larger voids. Tiny fluctuations evolve into structures spanning hundreds of millions of light years. And all of this happened naturally without any special mechanism, beyond gravity acting patiently across enormous timescales. There is something oddly comforting about that simplicity. The same force causing apples to fall from trees also sculpted giant holes into the architecture of the universe itself. No cosmic explosions required. No giant vacuum cleaners sweeping galaxies away. Just gravity doing what gravity always does, pulling, gathering, separating. One useful analogy involves bread dough while it rises in an oven. Inside the dough, bubbles of gas expand outward. The bread itself gets compressed into thin walls surrounding the bubbles. Over time, the empty spaces become larger, while the denser material forms interconnected structures around them. The cosmic web evolved similarly. Matter concentrated into filaments and walls. Voids expanded between them. Except instead of bread, the ingredients included dark matter, hydrogen gas, radiation, and approximately 13 billion years of cosmic evolution. Slightly harder recipe to follow, admittedly. Astronomers can actually simulate this process remarkably well today using supercomputers. Scientists begin with conditions matching measurements from the early universe, particularly the tiny fluctuations observed in the cosmic microwave background radiation. Then they allow gravity to evolve the simulated universe over billions of years. The results are astonishing. Filaments emerge naturally, clusters form, voids expand. The simulations end up resembling the actual observed cosmic web with surprising accuracy. This was one of the great triumphs of modern cosmology, because it demonstrated that large-scale structure formation could arise from simple physical laws acting over time. The universe did not need careful tuning to create its giant empty regions. They formed automatically. There is a beautiful inevitability to that idea. Given matter, gravity, and enough time, the cosmos naturally organizes itself into webs and voids, almost like frost forming on glass. Another strange consequence of void growth is that some voids may eventually dominate large portions of the universe visually. As cosmic expansion accelerates due to dark energy, distant galaxies drift farther apart. Over immense future timescales, galaxies outside our local gravitational group may disappear beyond the observable horizon entirely. Future civilizations, if any exist trillions of years from now, might see a much emptier universe than we do today. The cosmic web itself could gradually become harder to detect. In a sense, the universe may become increasingly isolated over time. That thought carries a peculiar loneliness to it. Right now, humanity exists during a cosmological era where the universe remains richly visible. We can observe distant galaxies, we can map large-scale structures, we can detect evidence of the Big Bang itself. But cosmic expansion slowly erases some of those clues. The universe changes its appearance with age, and voids are part of that story because they continue growing as expansion stretches space further. Interestingly, despite their emptiness, voids are not gravitationally irrelevant. Their low density influences the motion of surrounding matter in measurable ways. Galaxies near void boundaries experience gravitational flows away from the emptier regions toward denser structures. Astronomers sometimes refer to this as void evacuation, which sounds vaguely like a very serious plumbing emergency, affecting several billion light-years of space. But the principle is simple. Matter moves away from underdense regions because denser regions pull harder. One especially fascinating example involves our own galactic neighbourhood. The Milky Way itself participates in large-scale gravitational flows shaped partly by surrounding voids and dense structures. Galaxies do not simply drift randomly through space. They follow gravitational currents within the cosmic web. Some astronomers describe this almost like rivers and watersheds. Dense regions act like valleys attracting matter inward. Voids act more like high ground from which matter gradually flows away. The entire universe becomes dynamic rather than static. Matter streams along invisible gravitational pathways. This realization changed cosmology profoundly because it revealed that large-scale structure behaves almost organically. Not alive, of course, but evolving, changing, responding to gravity continuously. And once scientists understood how naturally voids formed, the giant empty regions stopped seeming mysterious in one sense and became even more mysterious in another. The existence of voids itself made sense, but their implications became enormous, because voids preserve information about the early universe extremely well. Dense regions become complicated quickly, galaxies collide, stars explode, black holes grow, chaotic interactions pile upon one another. Voids remain comparatively simple. They evolve more quietly. That makes them valuable cosmological laboratories. By studying voids, astronomers can test theories about dark matter, dark energy, cosmic expansion, and the geometry of the universe itself. The emptiest places became some of the cleanest windows into cosmic history. Again, the irony is wonderful. If you wanted to understand the universe better, you might expect scientists to focus exclusively on bright objects, exploding stars, quasars, giant galaxies. Instead, some of the most useful clues come from regions where almost nothing exists at all. It turns out emptiness is informative. Another detail worth appreciating is how extraordinarily long this entire process required. Human civilization spans only a few thousand years. Agriculture emerged roughly 10,000 years ago. The pyramids are ancient by human standards at around 4,500 years old. Meanwhile, cosmic voids evolved over billions of years. Gravity shaped them patiently, while stars formed and died countless times. Entire galaxies changed structure, while voids slowly expanded around them. The cosmos operates with almost unimaginable patience. There is no rush. Gravity simply continues working forever. And because gravity never completely stops, the cosmic web itself continues evolving today. Galaxies still migrate toward denser structures. Voids still expand. Matter still redistributes itself across colossal distances. Right now, while you sit quietly listening to this, entire galaxies are drifting along filaments shaped by gravitational forces that began acting shortly after the Big Bang. The motions are slow beyond ordinary human perception, but they are real. The universe never truly stands still, and perhaps the strangest part of all is that giant empty regions emerged not despite gravity, but because of it. Gravity built the cosmic web and accidentally created its enormous holes at the same time. The force responsible for gathering matter into stars and galaxies also produced some of the emptiest regions in existence. Creation and emptiness emerged together. The denser the filaments became, the emptier the voids grew. One shaped the other, which means cosmic voids are not mistakes in the structure of the universe. They are natural consequences of how gravity organizes reality itself. If you could somehow travel into the center of a large cosmic void, the first thing you would notice is not danger. It would be silence. Not ordinary earthly silence either. Not the quiet of snowfall or an empty road at night. Cosmic silence is something far stranger, because sound itself cannot travel through vacuum. There would be no wind, no distant echoes, no background hum. Nothing vibrating through the darkness except faint radiation and the occasional whisper of charged particles crossing unimaginable distances, and then there would be the sky, or perhaps more accurately the lack of sky. Human beings evolved beneath one of the brightest natural skies available in the universe. Even on moonless nights far from cities, Earth's heavens glow with thousands of visible stars. The Milky Way stretches overhead like spilled silver dust, because we live inside a large spiral galaxy packed densely with stars. Our night sky is crowded, inside a cosmic void that would change dramatically. Imagine drifting far from any major galaxy cluster, suspended deep within one of the loneliest regions in existence. The nearest large galaxies might sit hundreds of millions of light years away. Their light would appear faint and sparse. The sky would not blaze with thick star clouds or bright neighbouring galaxies. It would feel abandoned. Not entirely dark, of course. A few isolated galaxies might still glow dimly in the distance. Some nearby stars from your own local system could remain visible if you happened to originate from a void galaxy. But compared to Earth's rich celestial canopy, the heavens would seem hauntingly empty. The Milky Way itself might not even be visible depending on your location. That thought alone feels strangely unsettling. For thousands of years, human beings used the stars as emotional anchors. Ancient sailors navigated by them. Civilizations built mythologies around them. Entire calendars depended on them. Even today, people look upward searching for comfort, perspective, or occasionally proof that they are not the only ones awake at 3 a.m., thinking about awkward conversations from 7 years ago. But deep inside a cosmic void, the universe would appear profoundly isolated. There is an interesting psychological reason this bothers us so much. Humans instinctively associate light with safety and connection. Darkness suggests distance and uncertainty. Cosmic voids amplify those instincts to absurd levels because the emptiness is not local. It stretches for hundreds of millions of light years. Even the nearest galaxies could appear as tiny, faint smudges scattered across enormous blackness. And yet, despite all this emptiness, a cosmic void would not be completely featureless. One of the most fascinating discoveries astronomers made is that voids still contain galaxies, just far fewer than average. These are known as void galaxies, and they live unusually isolated lives compared to galaxies in crowded cosmic environments. To understand how strange this is, imagine two cities. One city is crowded and noisy, cars everywhere, buildings packed together, constant interaction. That resembles dense galaxy clusters where galaxies frequently pass near one another, collide, distort gravitationally, and exchange gas and stars. The second city is a tiny remote settlement in the middle of vast wilderness. Few neighbours, little traffic, long quiet stretches between interactions. That resembles life inside a cosmic void. Void galaxies often evolve more slowly and peacefully, because they avoid the violent collisions common in crowded regions of the universe. Galactic collisions sound dramatic because they are dramatic. When galaxies interact gravitationally, they can distort each other's shapes, trigger enormous bursts of star formation, and feed supermassive black holes at their centres. But inside voids, many galaxies remain comparatively untouched for billions of years. Astronomers sometimes study them almost like preserved ecosystems isolated from outside influence. And interestingly, void galaxies often appear bluer than galaxies in denser environments. That blue colour usually indicates ongoing star formation, because young massive stars burn hot and bright. In crowded clusters, galaxies frequently lose gas through interactions and eventually slow down star production. Inside voids, isolated galaxies may retain more gas for longer periods, allowing them to continue forming stars quietly over immense timescales. So while voids sound lifeless, they actually contain pockets of slow, gentle galactic evolution unfolding in relative solitude. There is something oddly peaceful about that image. Tiny islands of stars drifting through enormous darkness for billions of years with very few neighbours. Of course, if humans somehow attempted to travel across a cosmic void physically, the journey would be almost incomprehensibly difficult. Space travel already poses extreme challenges even within our own solar system. The distances between stars alone are enormous. Voyager 1, the fastest human-made object ever launched, has travelled for decades and still remains astonishingly close to Earth on galactic scales. Crossing intergalactic distances would require technologies far beyond anything humanity currently possesses. Crossing a major cosmic void, that enters truly absurd territory. Suppose you attempted to travel from one side of a 300 million light-year void to the other at the speed of light itself, which according to current physics remains impossible for objects with mass. Even then, the trip would require 300 million years. At ordinary spacecraft speeds, the journey becomes effectively meaningless compared to the lifespan of civilizations, species, or perhaps even entire evolutionary eras. Cosmic voids are so large that they redefine isolation itself, and this leads to one of the eeriest possibilities in astronomy. What if intelligent civilizations exist inside voids? It is a fascinating thought experiment, because civilizations living deep within underdense regions might perceive the universe very differently from us. On Earth, astronomers discovered cosmic expansion, partly because distant galaxies are visible everywhere. The night sky contains abundant clues about large-scale cosmic structure, but a civilization inside an extreme void could face observational limitations we barely consider. Imagine a species evolving around a star system located inside a sparse, isolated galaxy, far from major clusters. Their sky might reveal very few neighbouring galaxies. The broader cosmic web could remain almost invisible. Depending on the era in cosmic history, they might conclude their galaxy constitutes nearly the entire universe, simply because little else appears detectable. In fact, some cosmologists have speculated that future civilizations in our own distant cosmic future may face a similar problem. As dark energy accelerates cosmic expansion, distant galaxies will eventually drift beyond the observable horizon. The night sky could grow emptier over trillions of years. Future astronomers might lose access to evidence of cosmic expansion, or even the Big Bang itself, because the observable universe will appear increasingly isolated. In a strange way, cosmic voids offer glimpses of that lonely future already. Another remarkable detail about void interiors is how dark matter behaves there. Dark matter density inside voids is lower than average, but it never disappears completely. Invisible dark matter still threads faintly through these regions, subtly influencing the motion of galaxies and the behaviour of large-scale structures. This means that even in the emptiest places known, gravity continues operating quietly. The universe never becomes perfectly blank. Likewise, voids still contain extremely thin gas particles, mostly hydrogen. The density is astonishingly low compared to anything humans naturally experience. In some regions, there may be only a handful of particles per cubic metre. For comparison, Earth's atmosphere contains roughly 100 quadrillion molecules per cubic metre at sea level. Cosmic voids make even ordinary vacuum chambers seem crowded. And yet, despite their thinness, these sparse particles still matter scientifically, because they preserve information about cosmic evolution. Astronomers can study how light passes through void gas to understand the distribution of matter across enormous scales. Even near nothingness leaves detectable traces. One especially beautiful aspect of voids involves light itself. Light travelling through dense galaxy clusters often gets distorted gravitationally. Massive structures bend space-time according to Einstein's general relativity, warping the paths of photons crossing the cosmos. Voids influence light too, but differently. As light passes through underdense regions, subtle effects emerge because the gravitational landscape changes. Astronomers use these distortions to study dark energy and large-scale structure evolution, which means emptiness affects the journey of light across the universe. That idea feels wonderfully strange. Even absence changes reality. And while cosmic voids sound lonely from a human emotional perspective, the universe itself seems entirely comfortable with them. Nature does not fear emptiness the way we do. In fact, emptiness appears essential to cosmic structure. Without voids, galaxies could not organize into the web-like arrangements we observe today. Dense regions require sparse regions around them. The cosmic web depends on contrast. You see similar principles everywhere. A forest needs clearings, music needs pauses, conversation needs silence occasionally or everybody becomes exhausted, and someone inevitably starts talking about cryptocurrency at dinner. Structure emerges partly through absence. The universe applies this principle on scales beyond comprehension. Now, there is another important detail about cosmic voids that often surprises people. They are cold. Extremely cold, not because voids actively produce coldness, but because there are so few stars nearby to provide energy. Temperatures in deep intergalactic space already hover only a few degrees above absolute zero, mostly due to leftover radiation from the Big Bang known as the cosmic microwave background. Inside major voids, isolation intensifies that emptiness. The environment becomes almost unimaginably still and cold, and yet even there the universe never reaches perfect nothingness. Quantum fields continue fluctuating. Radiation crosses space endlessly. Dark matter drifts silently through the darkness. Tiny galaxies glow faintly like distant lanterns. The cosmos refuses absolute emptiness. This may actually be one of the deepest truths hidden inside cosmic voids. Human beings often imagine emptiness as the absence of existence altogether. But physics suggests perfect nothingness may not truly exist anywhere. Even vacuum contains structure. Fields, energy fluctuations, geometry. Space itself remains active. So when astronomers describe voids as empty, they mean empty relative to the rest of the universe. Not truly blank, just astonishingly sparse. That distinction matters because it changes the emotional feeling of these regions slightly. A cosmic void is not non-existence. It is simply existence stretched incredibly thin. There is still gravity, still light, still time, still the quiet unfolding of cosmic evolution, and perhaps that is why voids fascinate people so deeply. They force us to confront scale in a very unusual way. A single galaxy already feels immense. A galaxy cluster feels overwhelming. But a cosmic void flips the emotional script entirely. Instead of confronting overwhelming amounts of matter, we confront overwhelming absence. Distance itself becomes the dominant feature. Silence becomes architecture. Darkness becomes geography. And somewhere inside those giant empty expanses drift lonely galaxies quietly evolving, while the surrounding cosmic web glows impossibly far away. It is difficult not to feel small thinking about such places. Then again, astronomy has always excelled at making humanity feel simultaneously tiny and extraordinary at the same time. Tiny because the universe is so vast. Extraordinary because tiny creatures on one small planet somehow discovered these enormous silent regions at all. After all, cosmic voids cannot be seen directly with the naked eye. They reveal themselves only through careful maps, measurements, simulations, and decades of patient observation. Human beings built instruments capable of detecting the structure of the cosmos itself. We discovered that galaxies gather into rivers surrounding giant oceans of darkness. Among all the giant empty regions astronomers have discovered, one void became famous partly because of its enormous size, and partly because it sounded almost unbelievable when scientists first announced it, the Butter's Void. Even the name carries a certain atmosphere to it. Quiet, remote, slightly ominous, like the title of a forgotten science fiction novel sitting on a dusty shelf, somewhere beside a lamp that flickers for reasons nobody fully explains. But the Butter's Void is real. And it is one of the loneliest places humanity has ever discovered. Located roughly 700 million light-years from Earth in the direction of the constellation Butter's, this immense underdense region stretches approximately 330 million light-years across. To appreciate how absurdly large that is, it helps to compare it to familiar cosmic scales. Our Milky Way galaxy measures about 100,000 light-years wide. The distance to the neighbouring Andromeda galaxy is roughly 2.5 million light-years. The Butter's Void could swallow both galaxies thousands of times over, while still having room left for entire galaxy clusters. It is not merely large, it is cosmologically excessive. And what truly startled astronomers was not just its size, but its emptiness. When scientists first mapped the region in detail during the late 1970s and early 1980s, they expected to find many more galaxies scattered throughout it. Instead, they found remarkably few. At the time of its discovery, only around 60 galaxies were identified inside the void. 60. Now, that number sounds substantial by ordinary human standards. 60 apples fill a basket quite effectively. 60 ducks create logistical complications in public parks. 60 pizzas could feed an alarming number of astronomers during an all-night observation session. But cosmologically speaking, 60 galaxies inside such a gigantic region is astonishingly sparse. A normal region of comparable size would contain thousands of galaxies. Imagine standing in a major city and discovering that nearly every building for hundreds of kilometers in every direction had vanished, except for a few isolated houses still glowing quietly in the darkness. That gives at least a faint emotional approximation of the Butter's Void. Astronomers initially found the discovery difficult to process, because the scale of the emptiness challenged intuitive expectations about how matter should distribute itself across the cosmos. Some researchers jokingly referred to it as the Great Nothing. Others wondered whether observational errors or incomplete surveys might explain the apparent emptiness. Science tends to react cautiously to discoveries that sound suspiciously dramatic, and honestly, that caution is healthy. The universe already behaves strangely enough without researchers immediately announcing gigantic cosmic abysses every time a telescope produces unexpected data. But as observations improved, the Butter's Void remained unmistakably real. In fact, later surveys revealed that it was not unique. Many cosmic voids exist throughout the universe, though the boat's void remains one of the most famous because it captured public imagination so strongly. There is something deeply unsettling about giant emptiness. Human beings are generally more comfortable with objects than absences. A mountain feels comprehensible. A gigantic hole where a mountain should be feels strange. The Buddha's void triggered that emotional response on cosmic scales. People immediately began asking questions. How could such an enormous region form? Why is it so empty? Could something unusual have happened there? And naturally, because humanity cannot resist mystery, speculation spread quickly. Some imagined unknown physical processes sweeping galaxies away. Others wondered about exotic explanations involving dark energy or strange cosmological phenomena. A few people, predictably, proposed alien civilizations because apparently every sufficiently mysterious astronomical discovery eventually becomes somebody's extraterrestrial parking lot theory. In reality, the explanation appears less dramatic and somehow more fascinating at the same time. The Buddha's void formed naturally through the same gravitational processes shaping the entire cosmic web. Matter flowed toward denser regions over billions of years, leaving certain underdense areas increasingly sparse. The Buddha's void simply represents an especially extreme example of that process. Gravity built the surrounding structures so effectively that relatively little matter remained inside the void itself. In other words, the Buddha's void exists partly because nearby regions became too successful at collecting matter. Cosmic inequality reached extraordinary levels there. One especially eerie thing about the Buddha's void is imagining what the night sky might look like from inside it. Earth's sky feels rich because we reside inside a densely populated spiral galaxy. Even without telescopes, thousands of stars are visible under dark conditions. The Milky Way stretches overhead in luminous detail. Now imagine living inside a galaxy deep within the Buddha's void. The nearest major galaxies could lie staggeringly far away. The cosmic web itself would appear distant and sparse. Instead of glowing neighbouring galaxies filling the heavens, there might be only a few faint smudges scattered across enormous darkness. The universe would look profoundly lonely. And if intelligent life somehow evolved there, their understanding of cosmology might develop very differently from ours. This is one of the most fascinating thought experiments involving voids. Astronomy depends heavily on observation. Humanity discovered cosmic expansion, galaxy distribution, and large-scale structure because the observable universe around us contains abundant visible clues. But what if your galaxy existed in deep isolation? Suppose a civilization evolved inside a sparse void galaxy with very few visible neighbours. Would they conclude the universe contained only their galaxy? Would they detect cosmic expansion at all? Could they even discover the broader cosmic web without advanced instruments? Some cosmologists have seriously explored these questions because observational perspective shapes scientific understanding enormously. Humanity learned the universe was expanding because galaxies surround us visibly in every direction. But inside an extreme void, much of that evidence could appear weaker or harder to interpret. In a strange way, the Buddha's void reminds us how fortunate our observational position may actually be. We exist during a cosmic era where distant galaxies remain visible, and the large-scale structure of the universe can still be mapped. That will not remain true forever. As dark energy accelerates expansion, distant galaxies will eventually drift beyond the observable horizon. Future civilizations may inherit emptier skies than ours. The Buddha's void offers a glimpse of that loneliness already. Another remarkable detail about the void is how scientists study it despite its emptiness. You might think investigating regions containing relatively little matter would be difficult scientifically, but emptiness itself provides valuable information. Astronomers use galaxy surveys to map the structure surrounding the void. They analyse how galaxies move near its edges. They study how light passes through underdense regions. They compare observations against computer simulations of cosmic evolution. And all of this helps scientists test cosmological theories. For instance, voids provide useful environments for studying dark energy, because their low matter density makes certain large-scale expansion effects easier to detect. The emptier the region, the cleaner certain measurements become, which creates one of the great ironies of cosmology. Some of the best places to study the universe are the places containing almost nothing at all. The Bhuta's void also became culturally significant in ways astronomers probably did not entirely expect. Science fiction writers embraced it immediately because gigantic empty regions naturally trigger imagination. The idea of crossing a place where galaxies become rare and darkness stretches for hundreds of millions of light years feels emotionally powerful. And honestly, even scientists occasionally describe the void in ways bordering on poetic because the scale genuinely affects people psychologically. Terms like cosmic desert or intergalactic wilderness appear frequently. Not because researchers are trying to dramatize things unnecessarily, but because ordinary language struggles with such emptiness. There are few human experiences remotely comparable. Even Earth's most isolated environments remain biologically rich compared to cosmic voids. The middle of the Pacific Ocean still contains life everywhere. Deserts contain ecosystems. Antarctica still supports colonies of organisms. But the Bhuta's void spans distances so enormous and sparse that it approaches a level of isolation almost impossible for human minds to emotionally internalize. Yet despite all this emptiness, the void is not truly empty. That point remains crucial. A handful of galaxies still drift through it. Dark matter remains present at low density. Radiation crosses silently through the region. Sparse hydrogen gas floats between galaxies. The universe never quite permits absolute nothingness. In fact, later observations found more galaxies inside the Bhuta's void than initially detected, because improved instruments revealed faint objects early surveys missed. This happens often in astronomy. The universe enjoys reminding scientists that empty usually means we need better telescopes. Still, even after accounting for additional discoveries, the region remains extraordinarily underdense. One especially fascinating possibility is that studying galaxies inside the Bhuta's void may help astronomers understand how environment shapes galactic evolution. Galaxies and crowded clusters experience frequent interactions. They collide, merge, lose gas, and undergo intense gravitational disturbances. Void galaxies often avoid those experiences entirely. They evolve more quietly. Some retain primitive characteristics longer because their isolation shields them from cosmic chaos elsewhere. In a sense, the Bhuta's void preserves slower galactic histories, and that idea feels strangely peaceful. While crowded galaxy clusters crash and merge violently over billions of years, isolated void galaxies drift quietly through darkness, forming stars at gentler rates beneath sparse skies. The universe contains both chaos and stillness simultaneously. Another curious detail about the Bhuta's void is how it demonstrates the sheer scale of cosmic structure. People often think of galaxies as the primary large-scale objects in astronomy, but voids reveal that the spaces between structures matter just as much as the structures themselves. The universe resembles foam more than scatter, web more than randomness, and giant empty regions are essential components of that architecture. Without voids, the cosmic web could not exist. Dense filaments require sparse interiors around them. The Bhuta's void is not a flaw in the universe's design. It is part of the design itself. Again, not intentional design, of course. More like natural structure emerging inevitably from gravity, dark matter, and expansion over immense periods of time. The cosmos organized itself this way automatically. And somewhere along the process, it created one of the loneliest known regions in existence. There is something deeply humbling about realizing that places like the Bhuta's void exist at all. Human beings spend much of life surrounded by noise, movement, schedules, conversations, notifications, traffic, responsibilities, and the eternal mystery of why one sock always disappears during laundry. Meanwhile, out in the universe, there are regions so empty and quiet that hundreds of millions of light years pass with comparatively little happening at all. Gigantic expanses where galaxies become rare, where darkness dominates, where cosmic evolution unfolds slowly beneath sparse skies. And yet even there, gravity still works quietly. Time still passes. Light still travels. The universe remains active even in its loneliest places. Perhaps that is one reason the Boötes void continues fascinating people decades after its discovery. It reminds us that emptiness is not the absence of reality. It is simply another form of it. By now, the idea of cosmic voids probably feels familiar in a strange sort of way. Vast dark regions, sparse galaxies. Distances so enormous they almost stop feeling like distances at all, and become something more abstract, more atmospheric. But once astronomers accepted that these giant empty regions existed, another question naturally followed. Are they truly empty, or are we simply missing things hidden inside them? That possibility turns out to be more interesting than it first sounds, because astronomy has a long history of discovering objects that remained invisible for decades simply because our instruments were not sensitive enough. Entire galaxies once escaped detection. Black holes were inferred long before being observed directly. Dark matter still remains invisible today. So when scientists describe a region as empty, they always do so cautiously. The universe has a habit of hiding things in darkness and then revealing them later with an almost mischievous sense of timing. And cosmic voids are dark enough to hide quite a lot. At first, astronomers assumed the few galaxies found inside voids represented nearly everything there was to find. But as telescopes improved, additional faint galaxies gradually appeared in surveys. Not many, certainly nowhere near the densities seen in galaxy clusters. Still, enough to remind researchers that empty in cosmology is often a temporary statement. One especially important factor is brightness. Human beings instinctively associate existence with visibility, but astronomy constantly teaches the opposite lesson. Many objects in the universe emit very little light. Some galaxies contain relatively few stars and therefore glow only faintly against the darkness of space. These are called low-surface brightness galaxies, and they are surprisingly difficult to detect. A galaxy can be physically enormous while remaining visually dim if its stars spread thinly across space. Instead of appearing like a bright concentrated object, it becomes a diffuse smudge barely distinguishable from background darkness. Now imagine trying to detect such galaxies inside a giant cosmic void, where neighbouring reference points are sparse and distances are immense. It becomes very easy to miss things. In fact, astronomers suspect many faint dwarf galaxies may still remain undiscovered inside voids, simply because they emit too little light for current surveys to detect reliably. And dwarf galaxies are fascinating little objects. Compared to giants like the Milky Way, dwarf galaxies are tiny and often irregularly shaped. Some contain only a few billion stars or fewer, which sounds enormous until you remember our own galaxy contains hundreds of billions. Inside dense clusters, dwarf galaxies frequently get disrupted gravitationally by larger neighbours, but inside voids, they may survive in relative isolation for billions of years. Like tiny villages hidden deep within enormous wilderness, there is something oddly charming about that image. The universe's loneliest places still shelter small, quiet galaxies drifting through darkness almost unnoticed. But astronomers have considered even stranger possibilities. Could there be galaxies made mostly of dark matter with very few stars at all? These hypothetical objects are sometimes called dark galaxies. The idea emerged because dark matter appears to dominate the universe gravitationally, yet ordinary visible matter only forms part of the cosmic structure. In theory, certain dark matter halos might fail to form many stars, leaving behind nearly invisible galaxies detectable mainly through their gravitational effects or faint hydrogen gas emissions. If such objects exist in significant numbers, cosmic voids might be ideal places to hide them. After all, dense galaxy clusters tend to strip gas away from smaller systems and trigger interactions revealing their presence. Void environments are quieter and less disruptive. A dark galaxy drifting through a cosmic void could remain astonishingly difficult to detect. So far, evidence for true dark galaxies remains uncertain. Some candidate objects have appeared over the years, but many later turned out to contain faint stars after all. Still, the possibility continues fascinating astronomers because it highlights an important truth about cosmic voids. We define them partly by what we can observe, and observation has limits. The universe does not care whether human instruments can detect something easily. Another intriguing possibility involves rogue stars or isolated star systems wandering through void regions. Stars normally form inside galaxies because galaxies contain the dense gas clouds necessary for star formation. But galactic interactions can eject stars into intergalactic space. Collisions between galaxies sometimes fling stars outward at enormous velocities. Supermassive black holes can accelerate stars dramatically through gravitational interactions. As a result, some stars drift alone between galaxies. Astronomers call them intergalactic stars or rogue stars, depending on the context. Now imagine such stars crossing the immense darkness of a void. No nearby galaxy overhead, no crowded stellar neighbourhood, just isolated sunlight surrounded by incomprehensible emptiness. If planets orbited those stars, their inhabitants might experience skies unlike anything humans can imagine emotionally. No Milky Way stretching overhead, no neighbouring galaxies glowing brightly nearby, perhaps only a sparse scattering of distant points across enormous blackness. The psychological effect would be extraordinary. Human mythology, navigation and culture developed beneath rich star fields. Entire civilizations used the heavens as visual anchors for meaning and orientation. Inside a deep void, the cosmos itself might appear almost absent. There is also the fascinating question of gas hidden inside voids. Even extremely sparse regions still contain hydrogen gas drifting through intergalactic space. Detecting that gas is difficult because the densities are astonishingly low, but radio telescopes and spectroscopic measurements can reveal traces of it. Some researchers suspect filaments of diffuse matter still thread through void interiors more extensively than visible galaxies alone suggest. In other words, voids may not be completely disconnected regions. Faint hidden structures could still stretch across them invisibly. This idea becomes even more important when discussing dark matter. Dark matter does not emit light, yet it dominates much of the universe's mass. Computer simulations suggest dark matter should still exist inside voids at reduced densities, forming faint invisible scaffolding across even the emptiest regions, which means cosmic voids are not holes punched through reality. They are simply regions where visible matter became extraordinarily sparse. The underlying gravitational framework never entirely vanished. That distinction matters because it changes how astronomers think about emptiness itself. Void interiors still possess structure, still possess gravity, still possess physical processes unfolding slowly over billions of years. The universe refuses to create perfect nothingness. One especially clever method astronomers use to search for hidden matter. Inside voids involves studying how light passes through them. Light travelling across billions of light years interacts subtly with matter along its path. Gas clouds absorb certain wavelengths. Gravity bends trajectories slightly through gravitational lensing. Cosmic expansion shifts wavelengths gradually toward redder colours. By analysing these effects carefully, scientists can infer the presence of matter too faint to observe directly. It is rather like detecting invisible fingerprints across the cosmos. and occasionally these studies reveal more complexity inside voids than expected. Tiny galaxies, diffuse gas, weak filaments, subtle dark matter concentrations. The emptiness becomes textured rather than absolute. There is another wonderfully strange idea astronomers sometimes discuss involving failed galaxies. Not every dark matter halo necessarily succeeds at forming large visible galaxies. Some regions may have lacked enough gas density to ignite extensive star formation. Others may have lost gas early due to radiation from nearby cosmic events. This means the universe could contain numerous invisible or nearly invisible structures that never fully developed into ordinary galaxies, cosmic almosts, potential galaxies that never quite became luminous enough to announce themselves clearly. And if such objects exist, voids would again provide ideal hiding places. Dense clusters reveal structures through interactions and collisions. Void regions leave things comparatively undisturbed. It is the astronomical equivalent of finding forgotten cabins deep inside forests. Of course, there is always the temptation to push these ideas toward more speculative territory. Could advanced civilizations hide inside voids intentionally? Science fiction absolutely loves this possibility, because voids feel naturally mysterious. The immense distances and sparse environments create perfect settings for hidden empires, isolated megastructures, or ancient forgotten civilizations drifting through darkness. Realistically, though, voids would pose serious challenges for technological civilizations. Resources become sparse, neighbouring galaxies lie unimaginably far away. Travel between systems becomes even more difficult than usual intergalactic travel already is, which is saying something because ordinary intergalactic travel is approximately the cosmological equivalent of deciding to walk across an ocean carrying groceries. Still, the idea persists, partly because voids feel psychologically detached from the rest of the universe. They resemble cosmic wilderness, and humans instinctively imagine wilderness concealing secrets. Perhaps the strangest possibility of all is that voids may contain phenomena we have not even imagined properly yet. Astronomy repeatedly teaches humility in this regard. Every time humanity believes it, understands the cosmos reasonably well, the universe introduces something unexpected. Quasars, dark matter, dark energy, fast radio bursts, black holes merging loudly enough to shake space-time itself. Reality remains under no obligation to match our assumptions. So when astronomers map giant empty regions, they remain careful about declaring complete understanding. The visible emptiness is real, but complete emptiness? That becomes much harder to prove. One especially important lesson from modern cosmology is that visibility and existence are not the same thing. Most matter in the universe is invisible dark matter. Most energy may consist of dark energy. Even ordinary galaxies contain enormous invisible regions between stars. The universe is largely hidden by default. Human beings perceive only small portions directly. That realization changes how cosmic voids feel emotionally. At first, they seem frightening because they appear empty. But gradually you realize they are not empty at all. They are simply subtle, sparse, quiet, thinly populated, a cosmic whisper rather than a shout. And in some ways, those quieter environments may preserve information the louder regions erase. Crowded galaxy clusters become chaotic quickly. Interactions pile upon interactions. Histories grow complicated. Void environments evolve more gently, slower, cleaner. Which means hidden structures inside voids may preserve ancient clues about how the universe evolved after the Big Bang. There is something beautiful about that. The loneliest regions in existence may still contain forgotten traces of cosmic history, drifting quietly through darkness. Tiny galaxies no one noticed initially. Diffuse gas crossing impossible distances. Invisible dark matter shaping motion silently. Perhaps even structures humanity has not learned how to detect yet. And all of it unfolding inside regions so enormous that light itself requires hundreds of millions of years, merely to cross from one side to the other. The scale remains almost absurd no matter how long you think about it. Yet perhaps the most remarkable part is this. Human beings discovered the Bootes void and other giant cosmic holes only recently. We are still beginners at mapping the universe. Many surveys remain incomplete. Better instruments continue revealing fainter and more distant objects every year, which means the cosmos almost certainly still hides things from us, especially in the dark places, especially in the quiet ones. And now, having finally recognized the loneliest places in existence, astronomers have started asking an even stranger question. What if those empty regions contain clues more important than the galaxies surrounding them? For most of the history of astronomy, scientists focused their attention on bright things. That makes sense, really. Bright things are easier to notice. Stars explode dramatically. Galaxies glow across millions of light years. Quasars blaze brighter than entire galactic populations. Black holes launch jets so enormous they can stretch beyond their host galaxies themselves. Meanwhile, cosmic voids seem at first almost unhelpful. They contain comparatively little matter, fewer galaxies and far less visible activity. Yet over the past few decades, astronomers have slowly realised something rather surprising. The emptiest places in the universe may actually be some of the best places to study how the universe works. In certain ways, voids may tell us more than galaxies do. And the reason comes down to one very important problem. Galaxies are messy, beautiful certainly, interesting beyond measure, but messy. A galaxy is a chaotic environment where countless physical processes happen simultaneously. Stars form, stars explode, black holes consume matter, gas clouds collide, magnetic fields twist through space, galaxies merge violently with one another. Dark matter shapes motion invisibly. Radiation floods through enormous regions. Trying to study fundamental cosmological effects inside such environments can become difficult because everything overlaps. It is a little like trying to understand the movement of ocean currents while standing inside a crowded amusement park during fireworks. There is simply too much happening at once. Cosmic voids are different. Void environments are simpler, cleaner, quieter, and that quietness makes certain large-scale effects easier to detect. Astronomers sometimes compare this to studying ripples on water. If the surface is full of storms and crashing waves, tiny patterns become difficult to measure. But on calm water, subtle movements stand out clearly. Voids provide cosmology with calmer water. One of the biggest reasons this matters involves dark energy, the mysterious phenomenon causing the expansion of the universe to accelerate. Now, dark energy remains one of the strangest discoveries in modern science. In the late 1990s, astronomers studying distant supernovae realized something deeply unexpected. The universe was not merely expanding, its expansion was speeding up. That discovery genuinely shocked cosmologists because gravity should slow expansion over time. Matter attracts matter. The universe should gradually resist its own outward motion. Instead, something appears to be pushing space itself apart faster and faster. Scientists named this unknown effect dark energy, mostly because physics occasionally handles terrifying mysteries by assigning them names that sound suspiciously like rejected comic book villains. But despite the dramatic title, dark energy remains deeply mysterious. We do not fully understand what it is. We only know it dominates the large-scale behaviour of the cosmos, and cosmic voids may be one of the best tools for studying it. Why? Because voids contain relatively little ordinary matter. That means fewer gravitational complications interfere with measurements of cosmic expansion. Inside dense galaxy clusters, gravity strongly affects local motion. Galaxies orbit one another, collide and distort surrounding space-time. Inside voids, those effects weaken considerably. The emptiness allows astronomers to observe large-scale cosmic expansion more directly. In a strange way, voids act like enormous natural laboratories, where the universe becomes easier to study precisely because less is happening. That is wonderfully ironic. The quietest places reveal the loudest truths. One particularly important phenomenon involves how voids evolve over time. Remember, voids continue expanding as matter flows outward toward denser regions. But the rate at which voids grow depends partly on the overall expansion behavior of the universe itself. Dark energy influences that growth. By carefully measuring void sizes, shapes, and evolution across cosmic history, astronomers can test different cosmological models and narrow down possibilities for how dark energy behaves. Essentially, voids become giant measuring tools built directly into the structure of the universe. And because they span such enormous distances, they provide information about cosmic evolution on scales impossible to reproduce experimentally. Human beings cannot build laboratories millions of light years wide. The universe built them for us. Another reason voids are scientifically valuable involves gravity itself. Einstein's theory of general relativity remains extraordinarily successful, but scientists still test it constantly, because understanding gravity completely remains one of physics' deepest goals. Some alternative gravity theories predict slightly different behaviors inside low-density environments like cosmic voids. Dense galaxy clusters can hide subtle effects beneath layers of complicated interactions. Voids simplify things. Imagine testing how an object falls. Dropping it inside a hurricane would complicate measurements considerably. Dropping it in calm conditions works much better. Similarly, studying gravity in quieter cosmic environments sometimes reveals effects harder to detect elsewhere. Void research therefore helps scientists test whether Einstein's gravity behaves exactly as expected across enormous scales. So far, general relativity continues surviving these tests remarkably well. The universe keeps stubbornly agreeing with Einstein in ways that must be deeply satisfying if you happen to be Einstein, and somewhat intimidating if you're everybody else. Voids also help astronomers study dark matter distribution more clearly. Since ordinary matter becomes sparse inside voids, the subtle influence of dark matter sometimes stands out more distinctly in large-scale measurements. Researchers examine how galaxies move near void edges, how light bends passing through underdense regions, and how cosmic structures evolved over billions of years. All of this provides clues about invisible matter shaping the universe. Again, emptiness becomes useful precisely because it removes distractions. One especially fascinating technique involves studying something called the integrated Sachs-Wolf effect, which admittedly sounds less like cosmology and more like a law firm specializing in extremely complicated paperwork. But the underlying idea is elegant. As light from the early universe travels across enormous cosmic structures, the expansion of space and gravitational fields subtly alter the photon's energies. Dense regions and voids affect light differently. By analysing these tiny changes in cosmic microwave background radiation, astronomers can infer information about dark energy and large-scale structure growth. And cosmic voids produce measurable signatures in these observations. Even the emptiest regions leave fingerprints on ancient light crossing the cosmos. There is something deeply beautiful about that. A giant region containing comparatively little matter still influences photons travelling for billions of years across space. Absence itself alters the universe. Another important reason voids matter scientifically is that they preserve cleaner records of cosmic history. Dense regions become chaotic quickly. Galaxies merge repeatedly. Gas clouds collapse into stars. Black holes consume material. Energetic events reshape everything continuously. Voids evolve more gently. The sparse conditions mean fewer violent interactions occur. Structures inside voids often preserve information about earlier cosmic conditions more clearly than crowded environments do. In a way, voids function almost like protected archaeological sites. Dense galaxy clusters resemble crowded cities rebuilt repeatedly over ancient foundations. Void regions resemble remote landscapes where older structures survive relatively undisturbed. Astronomers can therefore use voids to investigate how the universe evolved shortly after the Big Bang. And because the cosmic web formed from tiny density fluctuations in the early universe, studying voids helps researchers understand those original fluctuations better. This becomes especially important when comparing observations against computer simulations. Modern cosmological simulations begin with conditions matching the early universe, measured through the cosmic microwave background. Scientists then allow gravity, dark matter, and expansion to evolve structures forward over billions of years. The resulting virtual universes produce cosmic webs remarkably similar to the real one, but small differences still matter enormously. By comparing actual void distributions against simulated ones, astronomers can test whether cosmological models accurately reproduce reality. Essentially, giant empty regions become statistical evidence about how the universe itself developed. And perhaps most intriguingly, voids may help answer one of the biggest questions in cosmology. Why does the universe look the way it does at all? That sounds philosophical at first, but it is also scientific. The large-scale structure of the cosmos depends on initial conditions shortly after the Big Bang combined with the behavior of gravity, dark matter, and dark energy over billions of years. Different physical laws would produce different cosmic webs. Different expansion histories would alter void growth. Different dark matter properties would reshape galaxy distributions. So when astronomers map void carefully, they are not simply cataloguing empty regions. They are reading the history of cosmic evolution itself. The universe encoded information into its structure. Voids preserve part of that record. There is another remarkable aspect to this. Voids are enormous. Absolutely enormous. That scale gives them statistical power. Individual galaxies can behave unpredictably because local conditions vary wildly. One galaxy might merge with neighbours repeatedly, while another evolves quietly in isolation. But giant voids average over immense distances. They reveal broader cosmic patterns less sensitive to local randomness. This makes them valuable for precision cosmology. Large structures reduce noise. Patterns emerge more clearly. One especially curious possibility scientists investigate is whether our own galaxy resides near a relatively underdense region. Some researchers have proposed that local void environments could subtly influence measurements of cosmic expansion rates. There is currently an ongoing debate in cosmology involving different measurements of the universe's expansion speed, known as the Hubble tension. Different methods produce slightly different results. One possible explanation involves local cosmic structure affecting observations. The idea remains controversial, but it highlights how important voids may be for understanding large-scale cosmic measurements accurately. Even our location within the cosmic web matters, and all of this emerges from studying places where almost nothing exists. That remains one of the most wonderful ironies in astronomy. Human beings instinctively focus on bright objects, yet the dark spaces between them often reveal deeper truths. You can see versions of this principle in ordinary life too. Sometimes silence reveals more than conversation. Sometimes pauses carry more meaning than words. Sometimes the shape of a thing depends most strongly on the spaces surrounding it. The universe appears to operate similarly. Without voids, the cosmic web would not exist. Without emptiness, galaxies could not organize into filaments and clusters. The structure depends on contrast. And the more astronomers study cosmic voids, the more they realize these giant silent regions are not secondary features of the universe. They are fundamental components of its architecture. The emptiness matters, not metaphorically, physically, scientifically, cosmologically. There is something strangely comforting about that realization. Human beings often fear emptiness because we associate it with absence or loss. But the cosmos treats emptiness differently. In the universe, empty regions shape everything around them. They guide motion, influence expansion, preserve ancient information, help reveal invisible physics. Even nothingness has structure, or at least near nothingness does. One of the strangest things about cosmic voids is that they are not frozen structures sitting passively in space like ancient fossils. They are alive with motion. Slow motion, certainly. The kind of slow motion only the universe can truly appreciate. Entire civilizations could rise and vanish while a void changes shape by only the tiniest fraction. But over billions of years, the changes become enormous. Cosmic voids are growing right now. At this very moment, matter continues drifting away from under-dense regions toward denser areas of the cosmic web. Galaxies migrate gradually along filaments. Space itself expands continuously. The giant empty regions become larger and emptier over time. In a way, the universe is still sorting itself, and the emptiness keeps spreading. This realization surprised astronomers because human intuition tends to imagine large cosmic structures as static. We look at photographs of galaxies and unconsciously treat the universe like a finished painting. But reality is much more dynamic. The cosmos behaves less like a completed sculpture and more like weather unfolding over impossible timescales. Galaxies move, clusters merge, stars explode, black holes grow, and voids expand slowly outward like bubbles in rising dough. The key reason voids grow comes back to gravity. Dense regions exert stronger gravitational pull than sparse regions. Matter therefore flows outward from void interiors towards surrounding filaments and clusters. Imagine placing tiny droplets of water across uneven terrain. The water naturally drains toward valleys, while higher areas become drier over time. The universe behaves similarly. Voids lose matter. Dense regions gain matter. And because the universe itself expands simultaneously, the process becomes even more dramatic. The emptiest regions stretch larger, while their densities continue dropping. Astronomers sometimes describe this process as void evacuation, which sounds surprisingly urgent for something occurring over billions of years. But the principle is straightforward. Matter gradually abandons the emptier neighborhoods. One especially interesting consequence of this process is that voids can merge together. Smaller voids growing beside one another eventually combine into larger structures. Their boundaries weaken, sparse regions connect. Over immense spans of time, giant supervoids emerge from the merger of many smaller underdense regions. It is somewhat like soap bubbles joining together in foam. The universe builds larger emptiness from smaller emptiness. And because dark energy accelerates cosmic expansion, this growth may become even more important over time. Now, dark energy is where things start becoming wonderfully strange again. When astronomers discovered in the late 1990s that the expansion of the universe was accelerating rather than slowing down, it completely changed cosmology. For centuries, gravity seemed simple enough conceptually. Matter attracts matter. Expansion, after the Big Bang, should gradually slow as gravity resists outward motion. Instead, observations showed the opposite. Distant galaxies are receding faster and faster over time. Something appears to be pushing space itself apart. Scientists named this mysterious effect dark energy, though that name mainly serves as a placeholder for, we know this exists, but honestly it remains deeply confusing. Dark energy now appears to dominate the large-scale behavior of the cosmos. Ordinary matter, the atoms making up stars, planets, people, sandwiches, and everything familiar, represents only a small fraction of the universe's total energy content. Dark energy makes up most of it. And cosmic voids may be one of the best places to study its effects. Why? Because voids contain relatively little matter. In dense galaxy clusters, gravity strongly shapes local motion. Galaxies orbit one another. Massive structures distort space-time significantly. All those interactions complicate measurements. Inside voids, the relative lack of matter allows cosmic expansion to dominate more clearly. The emptiness becomes sensitive to dark energy. In fact, some cosmologists think voids may expand faster than denser regions, precisely because dark energy acts more noticeably where gravity's opposing pull weakens. This creates a fascinating possibility. Void growth might help scientists understand the nature of dark energy itself. Astronomers carefully study how void sizes evolve across cosmic history. They compare observations against computer simulations using different cosmological models. Small differences in dark energy behavior produce measurable differences in how voids expand over billions of years. The universe essentially built giant natural experiments for us. Again, the irony remains delightful. The best places to study cosmic expansion are often the emptiest ones. There is another remarkable aspect to all this. Void expansion may actually influence the overall structure of the universe more significantly than people first assumed. Early cosmological models often treated the universe as smooth on extremely large scales, but modern observations reveal enormous complexity in how matter distributes itself, and some researchers have wondered whether giant voids could subtly affect measurements of cosmic expansion rates themselves. This idea connects to one of the most intriguing modern cosmological puzzles, the Hubble tension. Currently, different methods for measuring the expansion speed of the universe produce slightly different results. One method studies the cosmic microwave background radiation from the early universe. Another measures distances to nearby galaxies and supernovae directly. The answers disagree slightly, not dramatically, but enough to concern cosmologists because precise disagreement in science often hints at missing physics. One proposed explanation involves local cosmic structure. Suppose our galaxy resides near a relatively underdense region compared to the broader universe. In that case, local expansion behavior might differ slightly from the cosmic average. Essentially, nearby void environments could influence observations. The idea remains debated. Some scientists find it plausible, others think the effect is too small to explain the discrepancy fully. But the fact that voids even entered this discussion shows how important they have become in modern cosmology. The emptiest regions may affect how we measure the universe itself. That is quite a promotion for giant holes in space. Another strange effect of growing voids involves light. As photons travel through expanding voids across billions of light years, their energy shifts subtly due to changes in space-time geometry. This produces observable effects astronomers can measure carefully. One such phenomenon is the integrated Sachs-Wolf effect, which sounds like an extremely expensive law firm but is actually a subtle, cosmological signature involving how light interacts with evolving gravitational structures. As the universe expands under dark energy's influence, photons crossing giant voids gain or lose tiny amounts of energy differently than expected in a static universe. These distortions become evidence for cosmic acceleration itself. Even emptiness leaves fingerprints on light. And because voids span such enormous distances, their cumulative effects become measurable despite their low densities. One especially eerie implication of continued void growth concerns the far future of the universe. If dark energy continues accelerating expansion forever, distant galaxies will eventually disappear beyond the observable horizon. Over trillions of years, isolated galaxy groups may become effectively cut off from one another permanently. The cosmic web itself will thin visually. Voids will dominate more and more of observable space. Future observers may inhabit an increasingly lonely universe where evidence of large-scale cosmic structure becomes difficult or impossible to detect. Imagine civilizations born trillions of years from now inside isolated galactic remnants. They might see almost no external galaxies at all. The broader universe would appear empty. The Big Bang itself could become nearly impossible to infer observationally because the cosmic microwave background radiation will stretch into undetectably long wavelengths. In a sense, the universe gradually hides its own history over time, and growing voids play a major role in that process. There is something oddly melancholy about this future. Human beings happen to exist during a cosmological era where the universe remains richly observable. We can still see distant galaxies. We can map the cosmic web. We can detect ancient radiation left from the Big Bang itself. We arrived early enough to witness the structure, not too early when galaxies had not formed yet, not too late when expansion erased the evidence. That timing feels extraordinary. Of course, cosmic voids themselves are not causing dark energy. They are consequences of large-scale structure evolution combined with expansion. But they may amplify certain effects or help reveal underlying physics more clearly. Some speculative theories even explore whether the cumulative influence of voids could alter large-scale expansion behavior slightly through complex gravitational averaging effects. This area of research remains controversial and highly technical, but it highlights something important. Cosmologists still do not fully understand how structure, gravity, and expansion interact across enormous scales. The universe remains partially mysterious, and voids sit directly inside those mysteries. Another fascinating aspect of void growth is how it reshapes galaxy motion. Galaxies near void boundaries experience gravitational flows away from underdense regions toward filaments and clusters. Astronomers map these motions carefully because they reveal the invisible distribution of matter across space. In some ways, voids act almost like cosmic watersheds. Matter drains outward from them slowly over billions of years. The universe develops currents. Galaxies drift along invisible gravitational landscapes sculpted by dense regions and emptiness together. Even our Milky Way participates in these flows. We are not stationary observers sitting calmly inside a fixed universe. Our galaxy moves through the cosmic web influenced by surrounding structures, including nearby voids and massive galaxy concentrations. Everything moves, everything evolves, and all of it unfolds on scales so enormous that human minds naturally struggle to internalize them emotionally. Still, perhaps the most astonishing thing about growing voids is that they reveal how dynamic emptiness truly is. Humans often imagine emptiness as passive, but cosmic voids expand, evolve, merge, distort light, shape galactic motion, and help reveal the behavior of dark energy itself. The emptiness participates in cosmic evolution. That changes the emotional feeling of voids completely. They are not dead zones, not inactive gaps. They are dynamic components of the universe's architecture, continuously shaping and being shaped by the evolution of space-time itself. There is something deeply strange about empty space. Not just emotionally strange, though it certainly is that too. The idea of drifting through a region where galaxies become rare and darkness stretches across hundreds of millions of light years naturally unsettles the human imagination, but physically strange as well. Because when astronomers began studying cosmic voids more carefully, they realized emptiness changes things in subtle and surprising ways, especially light, especially time. And once Einstein entered the conversation, the entire idea of empty space became much more complicated than anyone expected. For most of human history, space was imagined as a passive stage, an empty backdrop where stars and planets simply existed. Time also seemed straightforward. Seconds ticked uniformly. Clocks marched forward steadily regardless of where you happened to be. Modern physics destroyed that comforting simplicity completely. According to Einstein's theory of general relativity, space and time are woven together into a single fabric called space-time. Massive objects warp this fabric through gravity. Planets orbit stars because they follow curves in space-time geometry. Light itself bends when passing near massive structures, which means empty regions behave differently from crowded ones. The universe is not just filled with objects. The geometry itself changes, and cosmic voids provide some of the clearest environments for observing those differences. Now, at first glance, you might assume emptier regions would simply contain less gravitational distortion. That part is true, but the consequences become surprisingly subtle. Imagine light beginning an immense journey across the universe. Perhaps it originates from a distant galaxy billions of light years away. For billions of years, the photons travel through the cosmic web, crossing clusters, filaments, and enormous voids before eventually reaching Earth. During that journey, space-time itself changes continuously. Dense galaxy clusters warp space-time strongly because of their enormous mass. Light passing near them bends slightly, a phenomenon called gravitational lensing. Voids influence light differently. Instead of strong gravitational wells, voids represent underdense regions where the gravitational landscape becomes comparatively shallow. And because the universe expands while light travels, strange things begin happening. One especially fascinating effect involves redshift. As space expands, light waves stretching across the cosmos also stretch. Their wavelengths grow longer, shifting toward the red end of the spectrum. This happens everywhere in the expanding universe, but large structures influence the process subtly. Inside dense regions, gravity slows local expansion somewhat because mass pulls matter together. Inside voids, there is less gravity resisting expansion. As a result, space inside voids may expand slightly more rapidly than denser regions around them. That means photons traveling through giant voids experience a slightly different space-time environment than photons crossing crowded galaxy clusters. The differences are tiny, extremely tiny. But across hundreds of millions or billions of light years, tiny effects accumulate into measurable changes. Astronomers can actually detect some of these signatures. One particularly important phenomenon is the integrated Sachs-Wolf effect, which we touched on earlier. The name still sounds vaguely like two physicists opening an aggressively complicated bakery together, but the concept itself is beautiful. As light from the early universe crosses evolving cosmic structures, the changing gravitational landscape alters photon energies slightly. If the universe were static, photons entering and leaving a gravitational region would gain and lose equal amounts of energy overall. But the universe is not static. Space expands, structures evolve, dark energy accelerates expansion, so the gravitational environment changes while the photons travel. Voids, therefore, leave subtle imprints on ancient light crossing them. The emptiness itself modifies the journey. There is something wonderfully eerie about that idea. A giant region containing comparatively little matter can still alter photons travelling for billions of years through space-time. Even nothingness bends the story of light. Another fascinating aspect involves temperature. Deep inside cosmic voids, temperatures become extraordinarily low because there are so few nearby stars or galaxies radiating energy. Intergalactic space already hovers only a few degrees above absolute zero, thanks mainly to the cosmic microwave background radiation left over from the Big Bang. Inside giant voids, the environment becomes even more isolated. The darkness feels colder conceptually as well as physically. And yet, despite that cold emptiness, time itself still flows normally for local observers. This is important because science fiction often portrays deep space as places where time behaves wildly or unpredictably. In reality, time dilation depends primarily on gravity and velocity. Inside a void, gravitational fields are weaker than in dense clusters because there is less nearby mass warping space-time strongly. That means clocks deep inside voids would actually tick very slightly faster relative to clocks inside stronger gravitational fields. The effect is tiny, incredibly tiny. You would never notice it directly during ordinary experience, but according to general relativity, it is real. Gravity slows time. Less gravity means slightly less slowing, which creates an amusingly strange possibility. In a purely technical sense, time passes a little differently inside giant empty regions than it does inside crowded galaxy clusters. The universe keeps adjusting reality subtly depending on where you are. There is no universal cosmic clock ticking identically everywhere. Einstein made sure of that. One especially interesting consequence of weak gravitational environments involves cosmic expansion itself. In dense regions, gravity partially resists expansion because matter pulls inward. Galaxy clusters remain gravitationally bound despite the universe expanding overall. Inside voids, there is much less matter resisting expansion. As a result, void regions effectively stretch more freely. Some cosmologists even describe voids as regions where cosmic expansion wins more decisively against gravity. The emptiness grows emptier partly because space itself expands more efficiently there, and over billions of years that difference becomes enormous. Voids widen, galaxies drift farther apart, darkness expands. This process also influences how observers inside voids might perceive the universe. Suppose an astronomer lived deep within a giant underdense region. The local expansion behavior they measured could differ slightly from observers in denser environments. In fact, some scientists have investigated whether humanity itself resides near a moderately underdense region, and whether that affects our cosmological measurements. The idea remains debated, but it highlights something profound. Location matters cosmologically. Where you exist within the cosmic web influences what the universe looks like to you. And because light requires time to travel, observing the universe always means looking backward into history. When we see a galaxy 1 billion light-years away, we observe it as it existed 1 billion years ago. The photons reaching Earth began their journey long before humans existed. Cosmic voids complicate this picture further, because the photons may cross enormous underdense regions during their journey. The emptiness becomes part of the observation itself. In a way, every image of the distant universe carries a hidden map of the structures the light crossed along the way. Voids become invisible participants in astronomy. Another deeply strange feature of empty space involves quantum physics. Even perfect vacuum is not truly empty according to quantum field theory. This is one of those statements that sounds fictional at first, but is very much part of modern physics. Quantum fields permeate all of space-time. Even in vacuum regions devoid of particles, those fields fluctuate constantly. Tiny temporary particle-antiparticle pairs appear and vanish continuously due to quantum uncertainty. This means empty space possesses energy. The vacuum itself is active, and inside cosmic voids, these quantum fields remain present despite the vast emptiness. The universe never becomes truly blank. There is something almost comforting about that. No matter how empty reality appears, there is always structure beneath the silence, always fluctuations, always fields, always motion hidden inside stillness. One particularly mysterious consequence of vacuum energy may connect directly to dark energy itself. Some physicists suspect dark energy arises from properties of empty space. The vacuum may contain intrinsic energy causing space-time expansion to accelerate. If that idea is correct, then cosmic voids become even stranger. The emptiest regions in existence may reveal the deepest properties of space-time itself. That possibility still remains unresolved, but it demonstrates how profoundly important emptiness has become in modern cosmology. The universe's greatest mysteries increasingly hide not inside stars or galaxies, but inside space itself. Another eerie detail about light travelling through voids is isolation. Photons crossing giant voids may travel for hundreds of millions of years without encountering major structures. Imagine a single particle of light beginning its journey near the edge of a galaxy cluster. Then imagine it crossing a giant void for perhaps 300 million years before finally encountering another major cosmic structure. 300 million years. On Earth, entire evolutionary eras occur during that interval. Dinosaurs appeared and vanished within shorter spans, yet for the photon, no time passes at all according to relativity. That detail always feels slightly unsettling. Light experiences no passage of time between emission and absorption. A photon crossing a cosmic void for hundreds of millions of years experiences the journey instantaneously from its own perspective. space and time behave differently at fundamental levels than human intuition expects, and cosmic voids magnify that strangeness because they expose light to such immense, uninterrupted distances. There is also a peculiar emotional effect when contemplating these enormous empty regions. Human beings evolved surrounded by environmental cues, trees, mountains, weather, voices, movement. Even deserts contain textures and landmarks. Void space removes almost everything. No nearby galaxies, few stars, almost no structure, just darkness and enormous scale. If a human somehow floated through such a region consciously, the psychological effect would likely be overwhelming. The emptiness itself becomes the dominant experience. Not danger exactly. Distance, silence, isolation beyond ordinary comprehension. And yet, scientifically, these quiet regions may hold some of the clearest clues about how space-time itself behaves. The emptiness strips away distractions. Dense regions become chaotic quickly. Too many interactions, too much gravity, too many overlapping processes. Voids simplify the universe enough for certain hidden patterns to emerge more clearly. There is a particular kind of fear that only astronomy can produce. Not the immediate fear of danger, not the sharp panic humans evolved for survival. Something slower, colder. The kind of fear that arrives quietly when you suddenly realize reality may be structured very differently than you assumed. And few ideas in cosmology produce that feeling more effectively than this one. What if the Milky Way exists near a giant cosmic void? At first, that may not sound especially alarming. After all, by now we have spent quite a long time discussing voids. We know they are natural parts of the cosmic web. We know they form through gravity. We know they influence expansion and galactic motion. But this particular possibility becomes unsettling because it directly affects how humanity measures the universe itself. It challenges our assumption that our local cosmic neighborhood is ordinary. And astronomy becomes much more complicated the moment you realize your observational position might not be typical. For centuries, humans repeatedly assumed we occupied some kind of central or privileged location in reality. Ancient civilizations often placed Earth at the center of the cosmos. Then we discovered Earth orbits the Sun. Then we discovered the Sun is merely one star among billions in the Milky Way. Then we learned the Milky Way itself is only one galaxy among countless others. Modern cosmology generally assumes no location in the universe is especially special overall. This idea is called the cosmological principle. On sufficiently large scales, the universe should look roughly similar everywhere. But roughly similar leaves room for local differences, and giant cosmic voids are very large local differences. One particularly intriguing proposal suggests that our galaxy may reside near a relatively underdense region, sometimes called the local void. Now, the local void is not nearly as extreme as the Butter's void, but it is still substantial. It represents a region near our galactic neighborhood containing fewer galaxies than expected. Astronomers discovered this sparse region while mapping nearby galaxy distributions. Surrounding structures appeared denser, while one direction seemed strangely underpopulated. At first, this simply looked like another ordinary feature of the cosmic web. But eventually some cosmologists began wondering whether local void environments could influence measurements of cosmic expansion itself. And this is where things become wonderfully strange. To measure how fast the universe expands, astronomers study distant galaxies and supernovae. By comparing distances and redshifts, they calculate the Hubble constant, which describes expansion rate. Except there is a problem. Different measurement methods produce slightly different answers. This disagreement is called the Hubble tension, and it has become one of the biggest puzzles in modern cosmology. Measurements based on the early universe, particularly the cosmic microwave background radiation, produce one value for the Hubble constant. Measurements based on nearby galaxies and supernovae produce a slightly higher value. The difference is not enormous, but it is persistent, and persistent discrepancies in physics tend to make scientists nervous in productive ways. Sometimes the problem turns out to involve measurement error. Sometimes it reveals entirely new physics. Nobody knows yet. Naturally, researchers began exploring every possible explanation. One idea proposed something fascinating. What if our region of the universe expands slightly differently because we live near an underdense area? Remember, voids contain less matter. Less matter means weaker local gravity resisting expansion. In principle, regions near large voids could experience slightly faster expansion than denser cosmic neighborhoods. If humanity happens to sit near such a region, our local measurements might differ subtly from the cosmic average. Essentially, the universe around us could appear to expand faster simply because of where we are located. That possibility is both scientifically interesting and psychologically unsettling, because it reminds us that observation always depends partly on perspective. Even in cosmology, there may be no perfectly neutral viewpoint. Now, it is important to say clearly that this idea remains debated. Most cosmologists do not think local void effects alone fully explain the Hubble tension. The observed discrepancies may require new physics involving dark energy, neutrinos, or something even stranger. Still, the fact that scientists seriously considered the possibility says a great deal about how important cosmic voids have become. The emptiest regions in the universe may influence our understanding of cosmic expansion itself, and the local void itself is genuinely interesting regardless of the Hubble tension. Astronomers estimate it spans hundreds of millions of light-years in certain directions and affects the motion of nearby galaxies. In fact, our Milky Way and neighbouring galaxies appear to move partly away from this underdense region toward denser structures elsewhere in the cosmic web. The void exerts influence not through pulling, but through relative absence of gravitational attraction. Dense regions pull harder. Matter drifts away from emptiness. The universe develops currents shaped partly by what is missing. There is something deeply strange about that. Emptiness directing motion. Silence shaping structure. And once scientists realized local voids influence galaxy motion, they began mapping cosmic flows more carefully. Galaxies do not drift randomly through space. They follow large-scale gravitational patterns generated by clusters, filaments, and voids together. Our galaxy itself participates in these motions. Right now, the Milky Way travels through the cosmic web, influenced by nearby massive structures like the Virgo cluster and the mysterious Great Attractor, as well as by neighbouring void regions. Everything moves, even galaxies, even galaxy clusters, even the emptiest regions continue evolving. One especially eerie implication of local voids concerns observation itself. Suppose humanity really does occupy a somewhat unusual location within the cosmic web. That would mean our measurements of the universe are shaped partly by local geography. Astronomy would resemble trying to understand Earth's climate while standing inside one specific valley. Your perspective would still contain valuable information, but it would not automatically represent the entire planet perfectly. Cosmologists work very hard to avoid this problem by averaging observations across enormous distances. Yet local structure always complicates measurements to some extent, and the larger the voids become, the more interesting those complications grow. There is also a philosophical discomfort hidden inside all this. Human beings prefer stable reference points. We want reality to feel objective and universal. The idea that our local cosmic environment could subtly distort our perception of the broader universe feels unsettling because it undermines intuitive certainty. What if the cosmos looks different elsewhere? Not merely visually different, but measurably different in subtle ways due to local structure. Now, fortunately, the cosmological principle still appears valid overall. On extremely large scales, the universe remains remarkably homogeneous. No evidence suggests humanity occupies a uniquely central or privileged location, but voids remind us that local environments matter. The cosmic web contains neighborhoods, some crowded, some sparse, some perhaps influencing observational results more than expected. There is another deeply strange aspect to all this involving cosmic isolation. If civilizations evolved deep inside giant voids, their understanding of cosmology might become severely limited. We touched on this idea earlier, but it becomes more unsettling the longer you think about it. Humanity discovered cosmic expansion because we can observe countless galaxies receding in all directions. The sky around us contains abundant evidence of large-scale structure. But imagine living inside an extreme void galaxy. Your night sky might contain only a few faint neighbouring galaxies. The broader cosmic web could remain almost invisible. Would such a civilization ever discover the universe's true large-scale structure? Could they infer the Big Bang accurately? Might they conclude their isolated galaxy represented nearly the entire cosmos? The possibility highlights how observational position shapes knowledge fundamentally. Even scientific truth depends partly on what the universe allows you to see. And this connects back to the frightening possibility involving our own location, not because living near a void is physically dangerous. Void regions are not cosmic predators waiting silently in darkness. The fear is subtler. It is epistemological, a fear about knowledge itself. What if our perspective is incomplete? What if the universe appears the way it does, partly because of where we happen to exist within the cosmic web? Astronomy repeatedly humbles humanity this way. Every time we believe we finally understand the universe clearly, new structures or effects emerge, complicating the picture. Dark matter changed cosmology. Dark energy changed it again. Now voids increasingly shape our understanding of cosmic expansion, structure formation, and observational limitations. The emptiness matters more than anyone expected. There is also something emotionally eerie about knowing our galaxy drifts beside enormous regions of comparative darkness. The local void is not visible dramatically in the night sky. You cannot point upward and identify a giant black hole-shaped emptiness overhead. Its existence emerges statistically through galaxy mapping, but once you know it is there, it subtly changes your perception of the universe. Nearby galaxies gather unevenly, large structures pull matter collectively, sparse regions stretch outward, quietly across unimaginable distances. The cosmos becomes textured, uneven, full of invisible architecture shaping everything around us. And perhaps the strangest part is that this architecture continues evolving right now. The local void slowly changes. Galaxies continue drifting. Expansion continues accelerating. The cosmic web itself remains dynamic rather than static. Human civilization exists during one brief moment inside that enormous unfolding process. A very brief moment. By now, cosmic voids may no longer feel like strange accidents hidden between galaxies. They feel structural, fundamental, almost inevitable. And that is exactly what modern cosmology has gradually revealed. The universe does not merely tolerate empty space. It depends on it. Without vast regions of comparative emptiness, the cosmic web itself could not exist. Galaxies would not organize into filaments. Clusters would not emerge the same way. Large-scale structure would look entirely different. In a very real sense, the universe needs empty space in order to create everything else. At first, this sounds paradoxical, because human beings instinctively associate value with presence rather than absence. We admire mountains, forests, oceans, cities, stars, planets. Nobody usually pauses dramatically beside an empty parking lot and whispers, "Ah yes, the true foundation of civilization." Although to be fair, parking availability does occasionally inspire spiritual experiences. Still, our brains evolved to focus on objects and activity. Empty regions feel secondary by comparison. Cosmology turns that instinct upside down. Because on the larger scales, emptiness is not secondary at all. It is architecture. The cosmic web forms through contrast. Matter gathers into dense structures while surrounding regions thin out. Filaments become visible precisely because voids separate them. Imagine trying to draw a picture using only solid colour without any gaps or contrast. Shapes would disappear into uniformity. Patterns require differences. The universe operates similarly. Clusters matter because voids exist around them. The emptiness defines the structure. There is a surprisingly simple analogy for this hidden everywhere in ordinary life. Music depends on silence. Without pauses between notes, sound collapses into noise. Rhythm itself emerges partly from absence. Language works similarly. Spaces between words allow meaning to exist. Conversations require pauses. Breathing requires empty moments between inhaling and exhaling. Even architecture depends heavily on emptiness. A room is useful because of the space inside it, not merely because walls exist around the edges. Doors matter because they create openings. Roads matter because they separate structures. Human civilization quietly relies on emptiness constantly without thinking much about it. The universe appears to do the same thing on cosmic scales. Void regions create the spacing necessary for galaxies and clusters to organize into larger patterns, and interestingly, the emptiness itself often becomes more stable than crowded regions. Dense galaxy clusters are violent places. Galaxies collide repeatedly. Stars explode. Black holes feed aggressively. Matter gets heated, stripped, compressed, and reshaped continuously. Voids evolve more quietly. Their relative emptiness protects them from chaos. In a strange way, the loneliest regions in existence may also be some of the calmest. That calmness turns out to matter scientifically, because voids preserve information crowded regions often erase. The early universe left faint fingerprints in the cosmic web. Dense structures complicate those fingerprints through billions of violent interactions. Voids preserve cleaner traces, so emptiness becomes memory. Again, the irony is beautiful. The quietest places remember the oldest stories. Another reason the universe needs empty space involves gravity itself. Gravity amplifies differences naturally. Dense regions attract more matter while sparse regions lose matter outward. This process creates self-organizing structure across enormous scales. Without underdense regions, gravity could not produce the web-like architecture we observe today. Everything would distribute differently. The cosmic web is essentially a conversation between matter and emptiness unfolding over billions of years. Dense regions shape voids. Voids shape dense regions. Neither exists meaningfully without the other, and because voids continue expanding over time, they influence the future evolution of the cosmos as well. As dark energy accelerates cosmic expansion, the universe gradually becomes more isolated on large scales. Galaxy clusters drift farther apart. Voids widen. The observable universe slowly grows emptier. In other words, emptiness is winning. Not violently, not suddenly, just patiently. The cosmos increasingly stretches itself apart. That realization can sound depressing initially, but there is another way to view it. The universe is not decaying into emptiness. It has always contained enormous emptiness. Void regions were fundamental almost from the beginning. The cosmic web emerged through imbalance and contrast naturally. Perhaps emptiness is not the opposite of cosmic structure. Perhaps it is part of the structure itself. One especially fascinating implication of this idea involves habitability. Human beings exist because matter concentrated efficiently in certain regions of the universe. Stars formed. Heavy elements emerged inside stellar furnaces. Planets condensed around young stars. Biology evolved. All of that required dense environments, but dense environments alone are not enough. The universe also needed room, expansion, separation. If matter had remained perfectly smooth after the Big Bang, galaxies may never have formed at all. Tiny density fluctuations combined with growing underdense regions allowed structure to emerge. The emptiness helped create conditions for complexity. which means every living creature ultimately owes part of its existence to giant cosmic voids. That is a wonderfully strange thought. The vast empty regions between galaxies helped make life possible. Another important detail is that voids may protect galaxies in certain ways. Extremely crowded environments can become hostile for stable galactic evolution. Frequent collisions disrupt structure. Intense radiation fields emerge. Gas gets stripped from galaxies by interactions with hot cluster material. Moderately isolated environments often provide calmer conditions. The Milky Way itself occupies a relatively comfortable location. We are not trapped in the centre of an ultra-dense cluster where galactic collisions occur constantly. Nor are we completely isolated inside a giant void. Our position appears balanced enough for long-term galactic stability. The universe seems to produce complexity most effectively through balance rather than extremes. Not too dense, not too empty, somewhere between. You see this pattern repeatedly in nature. Forests require open spaces. Ecosystems depend on balance between abundance and scarcity. Even human minds struggle in environments that are either overwhelmingly chaotic or completely devoid of stimulation. Reality often flourishes in intermediate conditions, and perhaps that helps explain why cosmic voids feel emotionally powerful to people. They represent extremes of emptiness beyond anything humans naturally experience. Deserts still contain life. Oceans teem with organisms. Even Antarctica supports ecosystems. But cosmic voids approach a kind of isolation that feels almost philosophical, despite being entirely physical. Distances dominate. Darkness dominates. Silence dominates. And yet the universe still uses those regions productively. Even emptiness contributes. One particularly beautiful example involves light itself. If the universe were packed uniformly with matter, light could not travel the way it does now. Large-scale transparency emerged partly because matter condensed into structures, while enormous regions remained relatively empty. The night sky exists because of voids too. That sounds odd initially, but think about it carefully. If stars filled space uniformly forever, every direction in the sky would blaze with light. This problem, known historically as Olbers' paradox, puzzled astronomers for centuries. Part of the solution involves cosmic expansion and the finite age of the universe. But large-scale structure matters too. Matter is clumped rather than evenly distributed. The darkness between stars is real. Void regions help preserve cosmic darkness itself, and darkness turns out to be essential for observation. Without dark skies, galaxies become difficult to detect. Without emptiness between structures, contrast vanishes. Even astronomy depends on cosmic silence. There is also something psychologically important about emptiness. Human beings often fear empty space because it confronts us with scale directly. Crowded environments provide reference points and emotional comfort. Void regions remove those anchors. Yet many people also find emptiness calming. Quiet rooms, open landscapes, night skies far from cities. Something about spaciousness allows the mind to slow down. Cosmic voids magnify that feeling to unimaginable scales, not because they are peaceful in any human sense, but because they reveal a universe unconcerned with filling every corner. The cosmos allows vast silence to exist, and perhaps that silence is necessary, not metaphorically, physically. Because the more astronomers study the large-scale structure of reality, the clearer one truth becomes. The universe is not built from objects alone. It is built from relationships between objects and emptiness together. Matter gathered into filaments because voids expanded around them. Galaxies formed because density varied. Structure emerged because the universe was uneven from the beginning. Perfect uniformity would have produced a far less interesting cosmos. Maybe no galaxies, maybe no stars, maybe no planets, possibly no observers at all. The tiny imperfections in the early universe changed everything. Slightly denser regions became galaxies. slightly emptier regions became voids, and together they created the architecture of reality we inhabit today. There is something deeply comforting about that idea. Existence emerged not from perfect order, but from imbalance and variation. The universe did not require flawless symmetry to create beauty or complexity. It required contrast. Another fascinating aspect of voids involves time. Dense regions evolve quickly because interactions happen constantly. Stars form rapidly, galaxies merge, black holes grow, chaos reshapes everything continuously. Voids evolve slowly, almost peacefully. Their emptiness stretches change across immense timescales. In a sense, voids preserve cosmic patience. The universe becomes quieter there, less hurried, less crowded, and perhaps that slowness matters too. Not every part of reality needs to burn brightly all the time. Some regions simply hold space between the brighter structures. The cosmos appears perfectly comfortable with that arrangement, and the farther astronomers look into the future, the more important emptiness becomes. As cosmic expansion continues accelerating, distant galaxies drift farther apart. The observable universe gradually grows darker and more isolated. Voids widen continuously. The future universe may become increasingly dominated by emptiness, not because something went wrong, but because emptiness was always one of the universe's defining features from the very beginning. The cosmic web itself depends on it, which means the giant holes between galaxies are not mistakes in creation. They are part of the framework holding everything else together, and once you begin seeing the universe that way, the darkness between galaxies no longer feels merely empty. It feels structural, necessary, almost quietly alive in its own strange cosmological way. And perhaps that is the most astonishing thing cosmic voids reveal. The universe does not fear emptiness, it builds with it. And so, after wandering through giant empty regions larger than entire superclusters, after crossing the dark rivers between galaxies and drifting beside the loneliest places humanity has ever discovered, we arrive back where we started, looking upward. Only now the night sky feels a little different, not because the stars changed, but because we know what surrounds them. For most of human history, the darkness between stars looks simple: empty background, blank space waiting for something brighter to happen. Ancient civilizations traced constellations across the heavens without realizing that behind those tiny points of light stretched an enormous hidden architecture made of filaments, clusters, and gigantic cosmic voids. Now we know better. The universe is not evenly filled. It breathes through contrast. Dense rivers of galaxies stretch across unimaginable distances while giant silent regions expand between them. Matter gathered together slowly over billions of years, leaving behind enormous emptiness that became just as important as the structures surrounding it. And perhaps that is the strangest lesson of all. The emptiness was never meaningless. Cosmic voids are not mistakes in the universe. They are not unfinished sections waiting to be filled someday. They are part of the design of reality itself. Gravity created them naturally. Expansion continues stretching them larger. Light crosses them differently. Galaxies move because of them. Even our understanding of dark energy may depend partly on studying these giant silent regions. The universe uses emptiness the way music uses silence. Structure emerges through spacing. Meaning appears through contrast. And somewhere inside one modest spiral galaxy, drifting quietly along an ordinary filament of the cosmic web, a small species evolved that became capable of noticing all of this. Honestly, that still feels miraculous. Human beings are tiny on cosmic scales. We live on a small rocky planet orbiting an ordinary star in the outer regions of one galaxy among billions, and yet somehow, through mathematics, telescopes, persistence, and endless curiosity, we discovered the architecture of the universe itself. We found the giant holes between galaxies. we learned that the cosmos resembles foam more than solid structure. We discovered that even emptiness evolves over time, and perhaps most wonderfully, we realized that silence itself can shape reality. There is something oddly comforting about that. People often imagine the universe as chaotic or violent because astronomy tends to focus on dramatic things: exploding stars, black holes, colliding galaxies. But cosmic voids reveal another side of reality entirely: patience, stillness, quiet evolution unfolding over billions of years. The emptiest places in existence are not rushing toward anything. They simply expand slowly while galaxies drift along distant filaments beneath sparse skies. And perhaps tonight, as you settle deeper into rest, there is something peaceful in remembering how vast the universe truly is. Right now, while cities sleep and clouds move across Earth and millions of ordinary human lives continue quietly onward, enormous cosmic voids drift through darkness, exactly as they have for billions of years. Light crosses them patiently, galaxies edge slowly away from their centres, the cosmic web stretches gently outward with the expansion of space-time itself, and far beyond anything the eye can see, the universe keeps rearranging its structure one tiny gravitational step at a time. Maybe that is why astronomy feels calming to so many people, not because space is small or comforting in any ordinary sense, but because the cosmos is so vast that it quietly places human worries into perspective. Somewhere out there are regions so empty that light can travel for hundreds of millions of years without meeting a major galaxy. Compared to that scale, the anxieties of a single afternoon begin to loosen their grip a little. The unfinished emails can wait. The awkward conversation from 6 years ago probably no longer requires additional analysis at 2:17 in the morning. Even the laundry may survive until tomorrow. The universe will continue evolving patiently regardless. And perhaps there is also something beautiful in realizing that emptiness itself is not failure. The cosmos does not try to fill every corner. It allows space for silence, space for darkness, space for distance. Without the voids, there would be no cosmic web. Without emptiness, the galaxies themselves would not arrange into the structures we see today. The universe builds with absence as much as presence. That idea feels surprisingly human too. After all, lives are shaped partly by pauses. Rest matters. Quiet matters. Empty moments matter. Sleep itself is a kind of temporary stillness that allows the mind to reorganize and recover. Maybe the cosmos understands that better than we do sometimes. And now, somewhere far beyond the Milky Way, beyond neighbouring clusters, beyond the glowing rivers of galaxies, the great voids continue stretching silently through the darkness. Cold, ancient, immense, not truly empty, never truly empty, because even there, light still travels, gravity still whispers across impossible distances, time still moves forward, and the universe keeps unfolding quietly between the stars.